At this very moment, the Sun is hurtling through interstellar space at approximately 52,000 miles per hour, dragging 8 planets, dozens of moons, and billions of smaller bodies, along with it on a journey that has lasted over 4.5 billion years. This motion is not gentle. It is a relentless plunge through a medium that most people never think about, a space between stars that appears empty but is anything but, and surrounding everything we have ever known, everything humanity has ever touched or built or dreamed about. There exists an invisible shield so vast that it dwarfs the distances between planets. This shield is generated by the Sun itself, a bubble of charged particles and magnetic fields extending billions of miles in every direction, deflecting and diverting the lethal radiation that floods interstellar space. Without this shield, the cosmic ray bombardment reaching Earth would be orders of magnitude higher. DNA would shatter more frequently, cancer rates would climb, the atmosphere itself would undergo chemical transformations that no human has ever witnessed. Here is what should unsettle you. This shield is not permanent. It is not guaranteed. It responds to conditions outside the solar system that the Sun cannot control, and evidence written in ancient ice cores, ocean sediments, and the rings of long-dead trees suggests that this shield has failed before. Not failed entirely, but contracted, weakened, compressed to a fraction of its normal size by encounters with something the solar system has passed through multiple times in its long journey around the galactic centre. Dense clouds of interstellar material, invisible to the naked eye but massive beyond comprehension, have squeezed the Sun's protective bubble until Earth itself lay exposed to the raw interstellar medium. When this happens, the boundary between inside and outside dissolves. The galaxy pours in. If you find yourself wanting to understand what happens when the Sun's shield fails, when the heliosphere that has protected every generation of life on this planet suddenly contracts beyond the orbit of Earth, then please consider liking and subscribing. It genuinely helps bring more content like this into existence. Are you ready? Let us begin. The Sun, for all its apparent stability, is a violent star. Every second it converts approximately 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. This energy radiates outward as light, heat, and something far less visible but equally important, a continuous stream of charged particles known as the solar wind. These particles, primarily protons and electrons stripped from hydrogen atoms in the Sun's corona, flow outward at speeds ranging from 250 to 500 miles per second, sometimes faster during solar storms. They carry with them the Sun's magnetic field, stretched and twisted into complex shapes that extend far beyond the orbits of all the planets. This solar wind does not simply dissipate into infinity. It pushes against something. Beyond the familiar confines of the solar system lies the interstellar medium, a thin but persistent soup of gas, dust, and cosmic radiation that fills the spaces between stars. Though incredibly diffuse by terrestrial standards, this medium exerts pressure. The solar wind, flowing outward, eventually reaches a boundary where its outward pressure exactly balances the inward pressure of the interstellar medium. This boundary defines the edge of the heliosphere. The heliosphere is not a sphere in the traditional sense. The Sun's motion through space compresses the side facing its direction of travel and stretches the trailing side into a long tail, creating a shape that some astronomers have compared to a windsock or a comet. The leading edge, called the heliopause, currently lies approximately 120 astronomical units from the Sun in the direction of travel. 1 astronomical unit equals the distance from Earth to the Sun, about 93 million miles. This means the protective boundary of the heliosphere, in its present configuration, extends more than 11 billion miles from the solar system's centre. Only 2 human-made objects have ever crossed this boundary. Voyager 1, launched in 1977, crossed the heliopause in August 2012. Voyager 2 followed in November 2018. Both spacecraft detected the transition unmistakably. Inside the heliosphere, they had measured solar wind particles flowing outward. Outside, they measured a dramatic increase in galactic cosmic rays and a complete change in the magnetic field direction. The boundary was real, measurable, and represented a genuine transition between the Sun's domain and the wider galaxy. What Voyager 1 and Voyager 2 confirmed is that the heliosphere acts as a shield against galactic cosmic rays. These cosmic rays are not the gentle radiation from distant stars. They are atomic nuclei, primarily protons but also heavier elements including iron and uranium, accelerated to nearly the speed of light by supernova explosions, colliding neutron stars, and the churning magnetic fields around black holes. A single galactic cosmic ray particle can carry more energy than a professional baseball thrown at major league speeds, concentrated into something smaller than an atom. When these particles strike the atmosphere, they trigger cascades of secondary particles that reach the surface. When they strike living tissue, they can sever DNA strands and damage cellular machinery. The heliosphere's magnetic field deflects and scatters incoming cosmic rays, reducing the flux that reaches the inner solar system by a factor of 3 to 4 compared to the interstellar environment. Earth's own magnetic field provides additional protection, and the atmosphere absorbs most of what remains. The combined effect means that humans at sea level receive roughly 1/10 the cosmic ray dose they would experience in interstellar space. This protection is so effective that most people live their entire lives without thinking about it. But the heliosphere's size depends on the balance between solar wind pressure pushing outward and interstellar medium pressure pushing inward. Change the interstellar pressure, and the heliosphere's boundaries shift. Increase that pressure dramatically, and the heliosphere contracts. Increase it enough, and the protective boundary retreats past the orbit of Earth itself. This is not a theoretical concern. The Sun is not stationary within the galaxy. It orbits the galactic centre at approximately 137 miles per second, completing one full orbit every 225 to 250 million years. This journey is not through empty space. The Milky Way contains vast structures of gas and dust, regions where the interstellar medium is thousands or even millions of times denser than the space the Sun currently occupies. These structures include giant molecular clouds, the stellar nurseries where new stars form, as well as smaller dense cloudlets, shells of material blown outward by ancient supernovae, and the remnants of disrupted nebulae. The Sun's path through the galaxy inevitably carries it through such regions. The local environment around the Sun has changed repeatedly over Earth's history. For the past few million years, the solar system has been passing through something called the local interstellar cloud, a wispy region of warm, partially ionized hydrogen about 30 light-years across. This cloud is relatively diffuse, only about 0.3 atoms per cubic centimetre, compared to the virtual vacuum of less than 0.01 atoms per cubic centimetre in the space the Sun occupied before entering it. Even this modest increase slightly compressed the heliosphere compared to its size in emptier space. But the local interstellar cloud is benign compared to what lies ahead. Observations of the Sun's trajectory suggest that within the next few thousand to tens of thousands of years, the solar system may exit the local interstellar cloud and encounter new structures. More dramatically, over millions of years, the Sun's orbit carries it through regions where densities can spike by factors of 100, 1,000, or more. When the interstellar density increases by a factor of 1,000, the heliosphere does not simply shrink proportionally, it collapses. The physics governing this collapse follows from basic pressure balance equations, but the implications are profound. In the present configuration, the heliopause lies at roughly 120 astronomical units, well beyond Neptune's orbit at 30 astronomical units. If interstellar density increased by a factor of 100, the heliopause would retreat to approximately 12 astronomical units, inside the orbit of Saturn. Increased density by a factor of 10,000, consistent with the outer edges of a giant molecular cloud, and the heliopause could retreat to less than 1 astronomical unit, inside Earth's orbit. In such a scenario, Earth would no longer reside within the heliosphere. Our planet would be directly immersed in the interstellar medium, exposed to galactic cosmic ray fluxes 3 to 4 times higher than normal, bathed in neutral hydrogen and helium from the cloud itself, and subjected to whatever dust and chemistry that cloud contains. The shield would be gone. The question of whether this has actually happened is not speculative. Geologists, geochemists, and astrophysicists have been piecing together evidence for decades. The answer they have found is disturbing. It has happened before, and not just once. The primary evidence comes from cosmogenic isotopes, rare atomic species created when galactic cosmic rays strike atoms in Earth's atmosphere or on its surface. The most important of these isotopes are beryllium-10, carbon-14, and chlorine-36. When a high-energy cosmic ray proton collides with an atmospheric nitrogen or oxygen atom, it shatters the nucleus and produces a spray of secondary particles. Some of these secondary particles are neutrons, which can then collide with other atoms to produce isotopes that would otherwise not exist. Carbon-14, for example, is produced when a cosmic ray-generated neutron strikes a nitrogen-14 atom. This carbon-14 then mixes into the atmosphere as carbon dioxide, is absorbed by plants and the oceans, and eventually gets deposited in tree rings, ocean sediments, and ice cores. The production rate of these isotopes is directly proportional to the cosmic ray flux reaching the atmosphere. Higher cosmic ray flux means more carbon-14, more beryllium-10, more chlorine-36. By measuring the concentrations of these isotopes in dated layers of ice cores drilled from Antarctica and Greenland, or in ocean sediment cores pulled from the seafloor, scientists can reconstruct a history of cosmic ray intensity stretching back hundreds of thousands to millions of years. What this record reveals is not a flat line. Cosmic ray intensity has varied significantly over Earth's history, and some of these variations cannot be explained by changes in solar activity or Earth's magnetic field alone. There are spikes and dips that suggest something more dramatic. Changes in the heliosphere's size, likely caused by encounters with dense interstellar material. One of the most compelling pieces of evidence emerged in 2024, when a team led by astrophysicist Merav Ofer at Boston University published a paper in the journal Nature Astronomy examining what would happen if the solar system encountered a dense interstellar cloud. Using sophisticated magnetohydrodynamic simulations, Ofer's team modelled the heliosphere's response to a cloud with hydrogen density around 3,000 atoms per cubic centimetre, roughly 10,000 times denser than the current local interstellar cloud. Such densities are found in cold, dense cloudlets within the broader interstellar medium. The simulation results were striking. When exposed to such a cloud, the heliosphere collapsed in approximately 10,000 years from its current size to a configuration where the heliopause retreated inside Earth's orbit. The termination shock, another boundary marking where the solar wind first slows down, retreated to less than 0.2 astronomical units from the Sun. For the duration of the cloud passage, which could last thousands to tens of thousands of years depending on cloud size and encounter geometry, Earth would exist outside the heliosphere entirely. But Ofer's team did not stop at simulation. They looked for observational evidence that such encounters had occurred. They found it in deep-sea sediment cores and Antarctic ice cores containing elevated levels of iron-60 and plutonium-244, two isotopes that cannot be produced naturally on Earth in significant quantities. Iron-60 has a half-life of 2.6 million years, and plutonium-244 has a half-life of 81 million years. Their presence in geological layers dated to between 2 and 3 million years ago, and again around 7 million years ago, had previously been attributed to nearby supernova explosions raining radioactive debris onto Earth. However, the correlation between these isotope spikes and changes in cosmogenic isotope production rates suggested a more complex picture. The supernovae that produced the iron-60 and plutonium-244 also likely created expanding shells of gas that the solar system later encountered. These shells, denser than the ambient interstellar medium, would have compressed the heliosphere precisely when the fallout from those supernovae was accumulating in Earth's sediments. The two signals, radioactive isotopes from the supernova themselves and elevated cosmic ray exposure from heliospheric compression, arrived together because they had the same cause. The timeline is particularly intriguing. Approximately 2 million years ago, Earth's climate underwent a dramatic shift. The ice ages intensified, the Pleistocene epoch began in earnest, and major changes occurred in African ecosystems that many researchers believe influenced human evolution. Whether these changes were influenced by elevated cosmic ray flux and altered atmospheric chemistry remains debated, but the coincidence is difficult to ignore. Even more provocative evidence emerged from studying specific cold, dense clouds in the Sun's galactic neighbourhood. Astronomers have catalogued dozens of local Leo cold clouds and similar structures within a few hundred light-years of the Sun. By reconstructing the Sun's path backward through time and modelling the motion of these clouds, researchers have attempted to identify past encounters. One particularly intriguing candidate is a passage through the edge of a dense cloud structure, approximately 2 to 3 million years ago, that aligns with the iron-60 and plutonium-244 evidence. Another potential encounter occurred approximately 7 million years ago, correlating with another iron-60 spike in the geological record. The uncertainty in these reconstructions is substantial. Cloud positions millions of years ago cannot be determined precisely, and the Sun's exact trajectory through the galaxy involves assumptions about gravitational influences and galactic dynamics that carry their own errors. But the pattern is consistent. When independent evidence suggests dense interstellar material was present, isotope records show signatures of elevated cosmic ray exposure. The heliosphere appears to have contracted at least twice in the past few million years, and likely many more times over Earth's 4 billion year history of hosting life. The implications for life on Earth are both subtle and profound. A temporary increase in galactic cosmic ray flux by a factor of 3 or 4, which is what heliospheric collapse would produce, does not immediately sterilize the planet. Earth's magnetic field would remain intact, providing some deflection of charged particles. The atmosphere would still absorb most of the secondary particle cascades. Life at the bottom of the ocean would be largely unaffected, but the effects would be real and measurable. Cosmic ray-induced ionization in the upper atmosphere affects atmospheric chemistry. Increased ionization enhances the production of nitrogen oxides, which catalyze the destruction of ozone. Multiple studies have modelled how elevated cosmic ray flux during heliospheric compression could deplete stratospheric ozone by 10 to 40%, depending on the duration and intensity of exposure. Ozone depletion increases surface ultraviolet radiation, which damages DNA, kills phytoplankton in the upper ocean, and stresses terrestrial ecosystems. The effects might not be catastrophic for a short passage lasting a few thousand years, but passages lasting tens of thousands of years or longer would impose sustained stress on the biosphere. Additionally, the cloud material itself would alter atmospheric chemistry. The interstellar medium is not pure hydrogen. It contains helium, trace amounts of heavier elements, and interstellar dust grains. If the heliosphere collapsed and Earth became directly immersed in cloud material, neutral hydrogen from the cloud would flow directly into the outer atmosphere. This hydrogen would react with oxygen to form water, but it would also participate in reactions that affect the ozone layer and upper atmospheric temperature. Dust grains entering the atmosphere would provide nucleation sites for cloud formation, potentially affecting climate. The precise effects depend on cloud composition and density, parameters that vary significantly between different interstellar structures. Some researchers have gone further, proposing that heliospheric collapse events correlate with mass extinctions in the fossil record. The evidence for this correlation is weak and contested, but the hypothesis cannot be dismissed entirely. Over Earth's history, the solar system has completed approximately 20 orbits around the galactic centre, passing through spiral arms, star-forming regions, and countless interstellar clouds. If each passage through a dense cloud lasted 10,000 to 100,000 years and imposed measurable stress on the biosphere, the cumulative effect over billions of years could be significant. The fossil record does show periodic fluctuations in extinction rates, and some researchers have attempted to correlate these fluctuations with the Sun's motion through the galaxy. The correlations are tantalizing but not yet conclusive. What is conclusive is that the heliosphere is not a permanent feature of the solar system. It is a dynamic structure that responds to external conditions, and those conditions have changed dramatically over Earth's history and will change again. The Sun is currently located in a relatively quiet neighbourhood of the galaxy, a region called the local bubble that was cleared of dense gas by multiple supernovae occurring 6 to 10 million years ago. This bubble, roughly 300 light-years in radius, is unusually empty compared to the galactic average. The local interstellar cloud that the Sun currently traverses is a wisp of material embedded within this larger bubble, perhaps part of the debris from those ancient supernovae, or an evaporating fragment of a larger structure. Eventually, the Sun will exit the local bubble. Current estimates suggest this will occur in approximately 10 to 50 million years, though the uncertainties are large. When it does, the solar system will encounter the denser gas that constitutes the normal interstellar medium in the Milky Way's disk. Even this ambient density, typically 1 atom per cubic centimetre, would compress the heliosphere to roughly half its current size. Encounters with denser structures would compress it further. More immediately, the Sun appears to be approaching the edge of the local interstellar cloud. Some observations suggest we may exit this cloud within the next few thousand years. What lies beyond is uncertain. The local interstellar cloud is embedded within a complex of other warm, partially ionized clouds, and the transition between these structures is not sharply defined. There may be denser cloudlets along the Sun's trajectory that would compress the heliosphere modestly. There may be relatively empty regions that would allow the heliosphere to expand. Predicting the exact sequence of encounters requires detailed mapping of the three-dimensional structure of the local interstellar medium, a task that remains incomplete despite decades of effort. The uncertainty is itself significant. Humanity has existed for only a few 100,000 years, and our written records span barely 5,000. Our technological civilization, capable of detecting and understanding these cosmic phenomena, has existed for less than 2 centuries. We have witnessed the heliosphere in only one configuration, under one set of interstellar conditions. We have no direct experience of what happens when those conditions change. What we have instead is inference, simulation, and the geological record. The simulations tell us that heliospheric collapse is physically possible and would occur on timescales short compared to geological epochs if the Sun encountered a sufficiently dense cloud. The geological record tells us that something changed cosmic ray exposure multiple times over the past few million years. The astronomical observations tell us that dense cloudlets exist in the local galactic neighbourhood, and that encounters with such structures are inevitable over sufficiently long timescales. The pieces form a coherent picture, even if many details remain uncertain. The Sun's protective bubble is not a permanent fortress. It is a weather phenomenon, waxing and waning in response to the medium through which the solar system moves. Sometimes the weather is calm and the bubble extends far beyond the planets. Sometimes the weather is stormy and the bubble contracts, exposing worlds that have never known anything but protection. Earth has weathered such storms before. Life has persisted through elevated cosmic ray flux, altered atmospheric chemistry, and whatever other effects dense cloud passages imposed. This resilience is encouraging but not necessarily comforting. Past life forms had no technology to protect, no digital infrastructure vulnerable to radiation-induced errors, no globalized civilization dependent on agricultural stability. Whatever stress those ancient encounters imposed was absorbed by ecosystems with millions of years to adapt. A modern encounter would be different, not because the physical effects would be more severe, but because human civilization has never experienced anything like it. Our entire technological and agricultural infrastructure has developed during a period of unusually stable cosmic conditions. The local environment around the Sun has been relatively benign for millions of years, and the heliosphere has maintained a configuration adequate to protect the inner solar system. We have built our world assuming this protection would continue. The geological record suggests this assumption may eventually be tested. Understanding the heliosphere requires understanding the Sun that creates it. The solar wind is not uniform. It varies in density, speed, and magnetic field strength over timescales ranging from hours to decades. During solar maximum, when sunspot activity peaks in the approximately 11-year solar cycle, the solar wind is denser and more energetic, the heliosphere expands slightly, and cosmic ray flux at Earth decreases measurably. During solar minimum, the reverse occurs. These fluctuations are small, typically changing cosmic ray intensity by 10 to 20%, but they are directly measurable by spacecraft and surface detectors. Longer-term variations also occur. The Sun appears to have periods of reduced activity lasting decades or centuries, such as the Maunder minimum between 1645 and 1715, when sunspots nearly vanished. During such periods, the heliosphere would contract modestly, and cosmic ray flux would increase. The geological record shows fluctuations in cosmogenic isotope production that may correspond to such extended minima, though separating solar variability from geomagnetic variability and interstellar medium changes requires careful analysis. The interplay between solar activity and interstellar pressure creates a complex system with multiple modes of variability. A dense interstellar cloud encounter would dominate over solar cycle variations, compressing the heliosphere regardless of whether the Sun was at maximum or minimum activity. But a modest increase in interstellar density combined with a prolonged solar minimum could produce effects greater than either factor alone. The system is nonlinear, and predicting its behaviour requires understanding multiple interacting processes. This complexity is why researchers have turned to detailed numerical simulations. Modelling the heliosphere requires solving the equations of magnetohydrodynamics, which describe the behaviour of electrically conducting fluids in magnetic fields. The solar wind is such a fluid, as is the ionised portion of the interstellar medium. Where they meet, the physics becomes intricate. Shock waves form, magnetic fields reconnect, instabilities develop at the boundary. Capturing these effects requires supercomputers running codes that have been refined over decades. The simulations performed by OFA's team and others like it divide space around the Sun into millions of small cells and track how density, velocity, pressure, temperature, and magnetic field evolve in each cell as the solar wind expands outward and interacts with incoming interstellar material. By varying the parameters of the incoming material, different interstellar encounters can be modelled. Low-density warm clouds, high-density cold clouds, magnetised structures, neutral hydrogen with embedded dust grains. Each scenario produces a different heliospheric response. These simulations have revealed surprises. The heliosphere does not simply shrink uniformly when squeezed by dense material. The compression is asymmetric, stronger on the leading edge where the solar system ploughs into the cloud and weaker on the trailing tail. Instabilities can develop at the heliopause, causing the boundary to ripple and flutter. In some scenarios, the heliosphere becomes highly variable, even if the incoming interstellar material is uniform, suggesting that the shield could flicker during a cloud passage rather than maintaining a stable compressed state. The timescale of compression is also faster than some early estimates suggested. When OFA's team simulated a sudden increase in interstellar density, the heliosphere responded within a few thousand years, not the tens of thousands of years that some previous calculations had predicted. This means that if the Sun were to enter a dense cloudlet while traversing the galaxy, Earth could transition from full heliospheric protection to full exposure within a span of time shorter than recorded human history. The change would not be instantaneous, but on geological or evolutionary timescales it would be abrupt. Recovery would be equally rapid once the cloud passage ended. As the Sun emerged from the dense material and interstellar pressure dropped, the heliosphere would reinflate, eventually returning to a configuration similar to its present state. For a cloud passage lasting 10,000 years, Earth might spend that entire period exposed to elevated cosmic ray flux, followed by a return to normal conditions that would persist until the next encounter. The frequency of such encounters depends on the structure of the interstellar medium along the Sun's orbit and the distribution of dense cloudlets within that structure. Current estimates suggest that encounters with clouds dense enough to compress the heliosphere inside Earth's orbit occur roughly once every 1 to 10 million years on average, though this figure is highly uncertain. Less dramatic compressions where the heliosphere shrinks but Earth remains inside likely occur more frequently. These estimates are based on surveys of the local interstellar medium and extrapolations of the Sun's orbital path. They carry substantial uncertainties because the three-dimensional structure of interstellar clouds is difficult to map. Clouds are detected primarily through their absorption of light from background stars or through radio and infrared emission, techniques that provide limited spatial resolution and often miss the smallest, densest structures. A cloudlet small enough to affect the solar system for only a few thousand years, but dense enough to collapse, the heliosphere might evade current surveys entirely. This means that future encounters cannot be predicted with confidence. We know they will occur. We do not know when the next one will occur, whether in thousands of years, millions of years, or some intermediate timescale. The uncertainty is irreducible with current technology, though future space missions designed to map the local interstellar medium in greater detail could narrow the range. For now, what matters is the recognition that the heliosphere is not permanent protection. It is a phenomenon dependent on conditions the Sun does not control. Those conditions have changed before and will change again. When they do, the effects will reach Earth, altering the radiation environment, atmospheric chemistry, and potentially the course of evolution itself. The evidence locked in ice cores and ocean sediments is a message from the past, written in isotopes that should not exist in the quantities observed unless something extraordinary happened. That something was the compression of the Sun's protective bubble, the temporary failure of a shield that most people do not even know exists. The message is clear. The threat to Earth does not always come from within the solar system. Sometimes it comes from the interstellar medium through which we endlessly travel, the cold, dark ocean between the stars that has shaped our planet's history in ways we are only beginning to understand. The sun continues its journey, carrying its family of worlds through that ocean, wrapped in a bubble of charged particles and magnetic fields that has served as armour for billions of years. That armour has held against the darkness more often than it has failed, but it has failed before, and the galaxy has poured through. The galaxy has poured through, and when it did, it left its signature on everything it touched. Understanding what that signature looks like, how it forms, and what consequences it carries requires examining the cosmic rays themselves, the particles that normally bounce harmlessly off the heliosphere, but that pour onto Earth when that shield compresses or collapses entirely. Cosmic rays are not rays at all. The name is a historical accident from the early 20th century, when scientists first detected mysterious ionizing radiation coming from above rather than from radioactive materials on the ground. Victor Hess, an Austrian physicist, discovered this radiation in 1912 by ascending in a hydrogen balloon to altitudes above 5,000 meters, carrying electrometers to measure ionization rates. He found that ionization increased with altitude, the opposite of what would occur if the radiation originated from Earth's surface. Something was bombarding the planet from space. Hess called it cosmic radiation, and the name stuck even after scientists determined that the radiation consisted not of electromagnetic waves but of particles, primarily protons stripped from hydrogen atoms, but also heavier atomic nuclei, electrons, and even small numbers of antimatter particles. These particles travel at tremendous velocities, many approaching the speed of light to within a fraction of a percent. A single cosmic ray proton might carry the kinetic energy of a baseball thrown by a professional pitcher, concentrated into a particle smaller than an atom. When such a particle strikes Earth's atmosphere, it does not simply stop. It collides with nitrogen or oxygen nuclei and produces a cascade of secondary particles, a shower that spreads outward as it descends, eventually reaching the surface as a diffuse spray of muons, electrons, and photons. Every second, several hundred of these secondary particles pass through your body, an invisible rain that has fallen since before humans existed. The sun produces its own cosmic rays, accelerated by solar flares and coronal mass ejections, but these solar energetic particles are generally lower in energy than their galactic counterparts. The truly dangerous cosmic rays, the ones that penetrate deepest into the atmosphere and produce the most extensive particle showers, originate outside the solar system entirely. They come from supernova explosions, from the shock fronts where stellar winds collide with interstellar gas, from the accretion disks around black holes, from the violent processes that occur throughout the Milky Way and beyond. These galactic cosmic rays have been accelerated by magnetic fields over millions of years, bouncing between shock fronts and gaining energy with each interaction, until they reach velocities where nothing in the solar system can accelerate them further. The heliosphere's primary job is deflecting these galactic cosmic rays. The sun's magnetic field, carried outward by the solar wind, creates a barrier that lower energy cosmic rays cannot penetrate. The field is not a solid wall, but a turbulent maze of magnetic irregularities that scatter incoming particles, redirecting them away from the inner solar system or trapping them in loops that eventually carry them back toward interstellar space. Higher energy cosmic rays can punch through this magnetic turbulence, which is why some galactic cosmic ray flux always reaches Earth, even under normal conditions. But the heliosphere blocks the majority of the galactic cosmic ray spectrum, particularly the particles in the energy range most effective at producing atmospheric ionization and surface radiation dose. When the heliosphere compresses, this filtering effect diminishes. The magnetic barrier moves closer to the sun, the region where cosmic rays are deflected shrinks, and a larger fraction of the incoming galactic flux reaches the inner planets. When the heliosphere compresses inside Earth's orbit entirely, the filtering effect disappears almost completely for Earth. The planet is left with only its own magnetic field and atmosphere as protection, and while these provide meaningful shielding, they are not designed to handle the full intensity of the galactic cosmic ray background. The atmosphere absorbs most incoming cosmic rays before they reach the surface, but the absorption process itself produces effects that propagate throughout the atmospheric column and leave traces in the geological record. The most significant of these effects involves the production of cosmogenic isotopes, atoms that do not form through normal geological or biological processes, but are created when cosmic ray particles collide with atmospheric nuclei. Beryllium-10 is perhaps the most important of these isotopes for reconstructing heliospheric history. It forms when cosmic ray protons or neutrons strike nitrogen or oxygen atoms in the upper atmosphere, shattering them and producing beryllium-10 as a byproduct. This isotope is radioactive, with a half-life of approximately 1.4 million years, long enough that it accumulates in geological deposits, but short enough that its presence indicates production within geologically recent times. Once formed in the atmosphere, beryllium-10 attaches to aerosol particles and precipitates out of the atmosphere within 1 to 2 years, falling with rain and snow onto the surface below. In polar regions, it becomes trapped in ice sheets, layer upon layer of frozen precipitation that preserves a continuous record of atmospheric beryllium-10 concentrations, stretching back hundreds of thousands of years. By drilling ice cores and measuring beryllium-10 concentrations at different depths, scientists can reconstruct the cosmic ray flux that reached Earth's atmosphere at different points in the past. Higher beryllium-10 concentrations indicate higher cosmic ray flux, which in turn indicates weaker heliospheric shielding. Carbon-14, more familiar to the public through radiocarbon dating, provides a complementary signal. This isotope forms when cosmic ray neutrons collide with nitrogen-14 in the atmosphere, converting it to carbon-14. Unlike beryllium-10, carbon-14 enters the carbon cycle, becoming incorporated into carbon dioxide, absorbed by plants during photosynthesis, and eventually finding its way into all living organisms and the organic matter they leave behind. Tree rings provide an annual record of atmospheric carbon-14 concentrations, extending back approximately 14,000 years using living and dead wood samples, with floating chronologies extending the record further into the past. Variations in carbon-14 production rate appear as deviations from the expected radioactive decay curve when dating organic materials, deviations that must be calibrated against independent records. Both isotopes respond to the same underlying cause, changes in the cosmic ray flux reaching Earth's atmosphere, and both isotopes have recorded spikes, anomalies, periods when production rates far exceeded normal values and then returned to baseline. Some of these spikes correlate with known solar activity minima, periods when reduced solar output temporarily weakened the heliosphere. The Maunder minimum of 1645 to 1715, when sunspot activity nearly ceased, appears in beryllium-10 and carbon-14 records as a modest increase in cosmogenic isotope production. The Dalton minimum of 1790 to 1830 produces a similar but smaller signal. These solar activity variations demonstrate that the isotope records do reflect heliospheric conditions, validating the approach. But some anomalies in the cosmogenic isotope record cannot be explained by solar activity variations. They are too large, too prolonged, or occur at times when other evidence suggests solar output was normal. These anomalies require a different explanation, and the compression or collapse of the heliosphere due to dense interstellar cloud encounters provides exactly the mechanism needed. The evidence Merav Ofer's team identified in sediment cores falls into this category. The Iron 60 signal from approximately 2 to 3 million years ago, coinciding with spikes in beryllium-10 and other cosmogenic isotopes, points to a period when the heliosphere was dramatically weakened for an extended time. Iron 60 itself is not a cosmogenic isotope. It is produced in supernovae rather than by cosmic ray interactions, but its presence in deep-sea sediments indicates that interstellar material was reaching Earth's surface during that period, material that would normally be filtered out by the heliosphere. The coincidence of elevated Iron 60 deposition with elevated cosmogenic isotope production strongly suggests that both signals reflect the same underlying cause, a severely compromised heliosphere that allowed both interstellar dust and galactic cosmic rays to reach Earth in quantities far exceeding normal levels. What would Earth have experienced during such an event? The immediate atmospheric effects would have been invisible to any hypothetical observer on the surface. Cosmic rays interact primarily with the upper atmosphere, tens of kilometers above the surface, where the air is thin enough that incoming particles can travel significant distances before colliding with atmospheric molecules. But the secondary particles produced by those collisions cascade downward, and the chemical changes they induce propagate through the entire atmospheric column. The most significant chemical effect involves ozone. Earth's ozone layer, concentrated in the stratosphere at altitudes between 15 and 35 kilometers, absorbs most of the sun's ultraviolet radiation before it reaches the surface. This absorption is what makes complex life possible on land. Without the ozone layer, ultraviolet radiation would sterilize exposed surfaces and make terrestrial ecosystems impossible. The ozone layer is maintained by a delicate balance of production and destruction processes, with ultraviolet radiation both creating and destroying ozone molecules through different photochemical pathways. Under normal conditions, these processes reach an equilibrium that maintains sufficient ozone to block most harmful ultraviolet wavelengths. Cosmic rays disrupt this equilibrium. When cosmic ray particles pass through the stratosphere, they ionize atmospheric molecules, splitting apart nitrogen and oxygen, and creating reactive species that catalytically destroy ozone. A single nitrogen oxide molecule created by cosmic ray ionization can destroy thousands of ozone molecules before being sequestered in a less reactive form. Under normal cosmic ray flux, this destruction pathway is minor compared to the other processes affecting ozone, a perturbation that the equilibrium accommodates without dramatic effect. But when cosmic ray flux increases by a factor of 2, or 5, or 10, the destruction pathway becomes dominant, and the ozone layer begins to thin. Models of atmospheric chemistry under enhanced cosmic ray flux predict significant ozone depletion during heliospheric compression events. The magnitude depends on how much the cosmic ray flux increases and how long the elevation persists. A doubling of galactic cosmic ray flux corresponding to a modest heliospheric compression, where Earth remains inside the reduced heliosphere, might produce ozone depletion of a few percent, comparable to the effects of chlorofluorocarbon pollution in the late 20th century. A tenfold increase in cosmic ray flux, corresponding to Earth's full exposure to the unshielded galactic environment, could produce ozone depletion of 50% or more, depending on how other atmospheric processes respond. The consequences of severe ozone depletion are well understood from studies of the Antarctic ozone hole and from modelling of hypothetical ozone-destroying events. Ultraviolet radiation reaching the surface increases dramatically, particularly in the biologically damaging ultraviolet B wavelengths between 280 and 315 nanometers. These wavelengths damage DNA directly, causing mutations, killing cells, and triggering skin cancers in exposed organisms. Phytoplankton in the upper ocean, which form the base of marine food chains, are particularly vulnerable because they live in the sunlit surface layer, where ultraviolet penetration is highest. Land plants can suffer leaf damage and reduced photosynthetic efficiency. Amphibians, whose moist skins offer little protection against radiation, are especially sensitive. During a heliospheric collapse lasting thousands of years, ecosystems would have to adapt to persistently elevated ultraviolet exposure. Evolution would favour protective pigmentation, behavioural changes that reduce surface exposure, and DNA repair mechanisms capable of handling increased mutation rates. Species unable to adapt would face population crashes and potential extinction. The pattern would not be random. It would selectively pressure certain lineages while leaving others relatively unaffected, creating the uneven extinction patterns that paleontologists observe in the fossil record during certain intervals. But ozone depletion is only one pathway through which cosmic rays affect the surface environment. Another involves climate, specifically the influence of cosmic rays on cloud formation and the broader radiative balance of the atmosphere. This is a more controversial area of research, with significant scientific debate about the magnitude and even the sign of cosmic ray effects on climate. The hypothesis dates to the late 1990s, when Danish physicist Henrik Svensmark proposed that cosmic rays influence cloud formation by ionizing atmospheric molecules and promoting the growth of cloud condensation nuclei. Clouds reflect incoming sunlight back to space, so an increase in cloud cover would cool the planet, while a decrease would warm it. If cosmic rays promote cloud formation, then periods of high cosmic ray flux should correspond to cooler global temperatures, and periods of low cosmic ray flux should correspond to warmer temperatures. The evidence for this hypothesis remains mixed. Some correlational studies have found relationships between cosmic ray flux and cloud cover, particularly for low-altitude clouds over the oceans. Experiments at the CERN Particle Physics Laboratory, specifically the cloud experiment that began operations in 2009, have demonstrated that ionizing radiation can indeed accelerate the formation of aerosol particles under controlled conditions. The particles formed are small sulfuric acid clusters that could potentially grow into cloud condensation nuclei. This establishes that the physical mechanism Svensmark proposed is real, at least in the laboratory. However, translating laboratory results to the actual atmosphere is complicated. The atmosphere contains many sources of aerosol particles and cloud condensation nuclei, including sea spray, dust, volcanic emissions, and biogenic particles from vegetation. Cosmic ray ionization is only one contributor to a complex system where many factors interact. Climate models that incorporate cosmic ray effects on cloud formation generally find the effect to be small compared to other climate forcings, though the models may not capture all relevant processes. For a heliospheric compression event, where cosmic ray flux increases by factors of several rather than the modest variations associated with solar cycles, the cloud formation effect could potentially be larger. A sustained increase in low-altitude cloud cover would cool the planet, potentially by several degrees, if the effect scaled linearly with cosmic ray flux. This cooling would compound other climate stresses and could contribute to glacial expansion, altered precipitation patterns, and shifts in ecological zones. The timing of heliospheric compression events has intriguing correlations with major climate transitions in Earth's history. The period from roughly 2.5 to 3 million years ago, when sediment cores record elevated interstellar material deposition, coincides with the intensification of northern hemisphere glaciation and the transition into the Pleistocene Ice Age pattern of cyclical glacial advances and retreats. The correlation does not prove causation. The onset of Pleistocene glaciation has been attributed to many factors, including the closure of the Central American Seaway, changes in atmospheric carbon dioxide and Milankovitch orbital cycles, but the possibility that cosmic ray effects contributed to climate destabilization during this period cannot be dismissed. More directly, cosmic rays affect the surface radiation environment in ways that go beyond chemical and climate effects. The secondary particles produced by cosmic ray interactions in the atmosphere eventually reach ground level, contributing to the natural background radiation that all terrestrial organisms experience. Under normal conditions, this contribution is modest. Cosmic ray secondary particles account for roughly 15% of the average human's annual radiation dose, comparable to the dose received from naturally occurring radon gas in homes. The biological effects are difficult to distinguish from the effects of other radiation sources because the contribution is small and the statistical signal is lost in the noise of other health factors. During a heliospheric compression event, the surface radiation dose from cosmic rays would increase in proportion to the cosmic ray flux reaching the atmosphere. A tenfold increase in cosmic ray flux would not produce a tenfold increase in surface dose, because the atmosphere absorbs more radiation as the total flux increases, maintaining some proportionality but with diminishing returns. Nevertheless, models suggest that surface radiation doses could increase by factors of 2 to 5 during severe heliospheric compression, depending on latitude, altitude, and atmospheric conditions. The effects of this elevated radiation would be subtle but pervasive. Mutation rates would increase for all organisms, accelerating the raw material of evolution, but also increasing the incidence of deleterious mutations and cancers. Radiation-sensitive cells, including reproductive cells and rapidly dividing tissues, would be disproportionately affected. Organisms with shorter generation times would accumulate mutations faster than those with longer generation times, potentially shifting the competitive balance between species. These effects would be difficult to detect in the fossil record because they affect population genetics rather than gross morphology, but they would nonetheless shape evolutionary trajectories over thousands of years. The cumulative picture that emerges from these individual effects is one of pervasive environmental stress. A heliospheric compression event would not produce a single catastrophic impact, like an asteroid strike or a supervolcano eruption. Instead, it would produce a sustained multi-pathway stress that would pressure ecosystems from several directions simultaneously. Ozone depletion would increase ultraviolet exposure. Cloud cover changes might alter climate. Elevated surface radiation would increase mutation rates. These stresses would interact with some organisms affected primarily by one pathway, and others by combinations. The result would be selective pressure that would reshape ecological communities over the duration of the event. The paleontological record from 2 to 3 million years ago shows exactly this pattern. This interval, spanning the late Pliocene and early Pleistocene, is marked by significant faunal and floral turnovers on multiple continents. African megafauna underwent major changes. with some lineages going extinct while others diversified. The closure of the Central American Seaway, which is conventionally blamed for much of this turnover, primarily affected marine ecosystems. The terrestrial changes require additional explanation. Climate cooling and drying certainly played a role, but the cause of that cooling remains debated. The coincidence of these biological changes with evidence of heliospheric compression invites the hypothesis that cosmic ray effects contributed to the environmental stresses driving evolution during this period. More dramatic evidence comes from earlier in Earth's history, during intervals when heliospheric compressions may have been more severe or more prolonged. The geological record preserves several mass extinction events whose causes remain poorly understood, events that do not correlate with known asteroid impacts or volcanism. The late Ordovician extinction, approximately 445 million years ago, which eliminated roughly 85% of marine species, has been attributed to glaciation and sea level change. But the trigger for that glaciation is unclear. The late Devonian extinction, roughly 375 million years ago, shows a pattern of prolonged environmental stress rather than sudden catastrophe, consistent with the sustained pressure a heliospheric compression would produce. These correlations are speculative, the result of searching for patterns in incomplete records with limited temporal resolution. The Iron-60 and cosmogenic isotope signals that provide relatively clear evidence for recent heliospheric compressions are not preserved or have not been detected in rocks billions of years old. But the hypothesis that heliospheric dynamics have influenced Earth's biological history throughout its existence is physically plausible, given that the Sun has completed dozens of orbits around the galactic centre since life first appeared and must have encountered dense interstellar material repeatedly during that time. The implications extend beyond Earth. Every planet in the solar system experiences the same heliospheric protection and would suffer the same exposure during compression events. Mars, with its thin atmosphere and absent global magnetic field, has even less secondary shielding than Earth. The Martian surface is already bathed in cosmic ray radiation, at rates roughly 2.5 times higher than Earth's surface under normal conditions. During a heliospheric compression, Martian surface radiation could increase to levels that would sterilize the uppermost soil layers and pose severe hazards to any hypothetical surface life or future human explorers. The outer planets, orbiting far from the Sun, might seem insulated from heliospheric dynamics, but they are not. The heliosphere extends well beyond Neptune under normal conditions, but compression could bring the heliopause inside the orbits of the outer planets, exposing their atmospheres and moons to unshielded galactic cosmic rays. Europa and Enceladus, moons with subsurface oceans that are considered possible habitats for extraterrestrial life, have ice shells that provide substantial shielding against cosmic rays, but the ice could become more radioactive over thousands of years of enhanced flux, with unknown consequences for any life beneath. The solar system is a connected system, bound together not just by gravity, but by the Sun's electromagnetic influence. When that influence weakens relative to external pressure, every world feels the change. The heliosphere is not Earth's shield alone, it is the shield for everything the Sun claims as its own, and that shield, for all its protective power, is contingent. It exists because the Sun generates a wind of charged particles and a magnetic field strong enough to push back against the interstellar medium. It persists because the interstellar medium through which the Sun travels is currently thin enough to be pushed back. Neither of these conditions is guaranteed. The Sun's output varies over its 11-year activity cycle, and over longer timescales as well. The interstellar medium varies across spatial scales from light-years down to distances the solar system crosses in decades. The heliosphere is a negotiated boundary, constantly adjusting to the balance of forces acting upon it, and sometimes that balance tips against the Sun. When it does, the consequences reach inward, touching every world, every atmosphere, every living thing that is sheltered unknowingly beneath a shield whose existence was, until recently, entirely unsuspected. The question that emerges from this understanding is not whether heliospheric compressions have occurred, but what determines how severe they become. The geological and cosmogenic evidence confirms that Earth has experienced enhanced cosmic ray flux multiple times in its history. The physical models explain how dense interstellar material can compress the heliosphere and emit galactic particles that normally never reach the inner solar system. But between a minor perturbation and a catastrophic collapse lies an enormous spectrum of possibilities, and the severity of any given event depends on factors that interact in ways scientists are only beginning to unravel. The density of the interstellar cloud is the most obvious variable. The local interstellar cloud through which the Sun currently travels has a density of roughly 0.3 atoms per cubic centimetre. This is dense by the standards of the local bubble, the cavity of hot, tenuous gas that surrounds the solar neighbourhood, but it is thin compared to the molecular clouds that populate the galaxy's spiral arms. A typical molecular cloud contains hundreds of atoms per cubic centimetre. The densest cores, the regions where new stars are actively forming, can reach densities of 1 million atoms per cubic centimetre or more. The heliosphere responds to density increases in a nonlinear fashion. Doubling the external density does not simply halve the heliospheric radius. The relationship involves the square root of the density ratio under simplified pressure balance conditions. But the real dynamics are more complex because the heliosphere is not a static bubble but a flowing system with shocks, turbulence and magnetic field structures that respond differently to different types of external pressure. The temperature of the interstellar medium matters as well because temperature determines the thermal pressure contribution independent of density. Hot gas exerts more pressure per particle than cold gas. The local bubble's extreme temperatures, roughly 1 million Kelvin, mean that even its very low density produces significant pressure. When the Sun encounters a cold molecular cloud, the thermal pressure contribution decreases, but the ram pressure increases dramatically because cold clouds tend to have higher densities and often different velocities relative to the Sun's motion. The interplay between thermal and ram pressure creates compression scenarios that differ qualitatively depending on the type of interstellar environment. The magnetic field structure of the interstellar medium introduces another layer of complexity. The heliosphere does not simply push against neutral gas. It interacts with the magnetized plasma of the interstellar medium through magnetic reconnection, current sheets, and field draping. A strongly magnetized interstellar cloud could compress the heliosphere more effectively than a weakly magnetized cloud of the same density, because magnetic pressure adds to the total external force. Conversely, certain magnetic field orientations might allow the heliospheric field to couple with the interstellar field in ways that stabilize the boundary rather than collapsing it. The magnetic field direction changes on scales comparable to the heliosphere's size, meaning that the compression dynamics could shift over timescales of decades as the Sun moves through differently oriented field regions within a single cloud. The velocity of the Sun relative to the interstellar material determines the ram pressure, which scales with the square of the relative velocity. The Sun currently moves through the local interstellar cloud at approximately 26 km per second, a velocity that has remained relatively stable over the period of residence within the cloud. But different clouds move at different velocities, and the Sun's own velocity through the galaxy is not constant. The solar system bobs up and down through the galactic disk as it orbits, completing a vertical oscillation roughly every 70 million years. During passages through the disk's mid-plane, the Sun is more likely to encounter the dense molecular clouds that concentrate there. The velocity component perpendicular to the disk adds to the relative motion through any cloud material, potentially increasing ram pressure during these passage events. Perhaps most critically, the solar wind's strength determines how much outward pressure the heliosphere can generate to oppose external compression. The solar wind is not constant. The 11-year solar activity cycle modulates the wind speed, density, and magnetic field strength, creating variations in heliospheric size on decadal timescales. During solar maximum, the heliosphere is slightly larger and more resistant to compression. During solar minimum, the reduced wind allows the heliosphere to contract modestly, even without any change in external conditions. Over longer timescales, the Sun's activity may vary more dramatically. Solar-type stars younger than the Sun tend to be more active, with stronger winds and more robust magnetospheres. As stars age, their rotation slows and their magnetic activity decreases. The Sun today generates a weaker wind than it did billions of years ago, meaning the heliosphere was likely larger and more resistant to compression in the distant past when life was first establishing itself on Earth. But there are intervals in the recent geological past when the Sun appears to have entered extended periods of reduced activity far more profound than the typical solar minimum. The Maunder minimum from roughly 1645 to 1715 saw sunspot numbers drop to near zero for decades, suggesting a dramatic reduction in solar magnetic activity. Ice core records show modest increases in cosmogenic isotopes during this period, consistent with a weakened heliospheric shield admitting slightly more galactic cosmic rays. The Maunder minimum occurred without any known change in the interstellar environment, demonstrating that the heliosphere can weaken from internal causes alone. A coincidence of reduced solar activity and enhanced external pressure could produce compression far more severe than either factor would cause independently. The worst-case scenario emerges from the convergence of multiple unfavourable factors. Imagine the Sun entering a dense molecular cloud during a period of extended solar minimum, with the cloud's magnetic field oriented to maximise compression at a relative velocity that produces strong ram pressure. Each factor multiplies the others. The heliospheric radius could collapse from over 100 astronomical units to a few astronomical units within decades. The termination shock could retreat inside the orbit of Jupiter. The heliopause could approach Earth's orbit itself. Such a scenario would not merely increase cosmic ray flux, it would fundamentally transform the space environment of the inner solar system, exposing planets to the full force of the galactic radiation field with virtually no filtering. How severe could that exposure become? Under normal conditions, Earth's surface receives a cosmic ray dose of roughly 0.3 millisieverts per year from the galactic component. After the combined filtering of the heliosphere, the magnetosphere and the atmosphere has removed most of the primary particles. Space agencies consider 1 millisievert per year a safe limit for members of the public, while astronauts are permitted exposures up to 50 millisieverts per year during missions, reflecting the occupational hazard of spaceflight. A moderate heliospheric compression, similar to what Earth likely experienced during passage through the local interstellar cloud's denser regions, might double or triple the galactic cosmic ray flux at Earth. Most of that increase would be absorbed by the atmosphere and magnetosphere, producing perhaps a 20 to 30% increase in surface dose rates, from 0.3 to perhaps 0.4 millisieverts per year from the galactic component. This is measurable, but not catastrophic, comparable to moving from sea level to a mountain city where thinner air provides less atmospheric shielding. A severe compression that retreated the heliopause to inside 10 astronomical units would increase the cosmic ray flux by an order of magnitude or more. The atmosphere would still provide substantial shielding, and the magnetosphere would still deflect many charged particles. But the surface dose rates could increase to several millisieverts per year. This remains below acutely dangerous levels for individual humans, but population-wide effects would emerge over generations. Cancer rates would increase measurably, mutation rates in all species would rise, the biosphere would experience a sustained genetic stress, unlike anything in recorded human history, though still within the range that life has apparently survived during past compression events. The extreme scenario, with the heliosphere collapse to the point where the interstellar medium directly contacts the magnetopause, would expose Earth to cosmic ray fluxes tens of times higher than normal. Surface dose rates could reach tens of millisieverts per year, approaching the occupational limits for radiation workers as a background exposure experienced by everyone on the planet. At these levels, health effects would be significant across all populations. Childhood cancer rates would rise substantially. Developmental abnormalities would increase. Agricultural productivity would suffer as crops experienced higher mutation rates and radiation damage to sensitive tissues. The human species would survive, but civilization would face a chronic health crisis lasting as long as the compression persisted, potentially thousands of years. But even this extreme scenario represents only the direct radiation effect. The secondary consequences of heliospheric collapse could prove equally significant through mechanisms that operate on the atmosphere itself. Galactic cosmic rays, particularly the high-energy protons that constitute the majority of the flux, initiate nuclear spallation reactions when they strike atmospheric molecules. These reactions produce cascades of secondary particles, including neutrons, pions, and muons, that carry the energy of the primary particle downward through the atmosphere. But the spallation reactions also produce specific isotopes that do not normally exist in the atmosphere. Beryllium-10 and carbon-14, the isotopes used to trace past cosmic ray flux in ice cores and tree rings, are products of cosmic ray spallation of nitrogen and oxygen in the stratosphere. Their production rates scale with the cosmic ray flux, which is why they serve as proxies for heliospheric conditions. These isotopes are chemically reactive and enter the biosphere through precipitation and carbon cycling. Their radioactivity contributes slightly to background radiation exposure, but their quantities, even during compression events, remain too small to cause significant direct harm. However, the spallation process also produces other molecules that do affect atmospheric chemistry. Nitrogen oxides, or NOx, are produced when cosmic ray cascades break apart nitrogen molecules in the stratosphere. Nitrogen oxides are catalysts for ozone destruction. A sustained increase in cosmic ray flux would produce sustained elevated nitrogen oxide concentrations in the stratosphere, leading to progressive ozone layer depletion. The ozone layer absorbs virtually all solar ultraviolet radiation in the UVC band, the most biologically damaging wavelengths, and most radiation in the UVB band. Ozone depletion allows more UVB radiation to reach the surface, causing increased rates of skin cancer, cataracts, and immune suppression in humans, as well as damage to phytoplankton, amphibians, and other UV-sensitive organisms. The ozone hole that formed over Antarctica due to chlorofluorocarbon pollution demonstrated how sensitive ecosystems are to even modest increases in UV exposure. The phytoplankton productivity declines measured during peak ozone depletion had implications for the entire marine food web. A heliospheric compression lasting centuries could produce sustained ozone depletion exceeding anything caused by industrial pollutants. Models suggest that a tenfold increase in cosmic ray flux could reduce stratospheric ozone by 30 to 50% globally, with larger depletions at high latitudes where cosmic ray penetration is greatest due to weaker magnetic shielding. The resulting UV increase would stress photosynthetic organisms on land and in the surface ocean, potentially reducing primary productivity and cascading through food webs to affect every level of the biosphere. The atmospheric ionization produced by cosmic rays has another potential effect that remains controversial, but physically plausible. Ionization creates charged particles in the troposphere that can serve as nucleation sites for cloud droplet formation. The hypothesis that cosmic ray flux modulates cloud cover, and thus climate, was proposed by Henrik Svensmark in the 1990s and has been debated ever since. The mechanism would work as follows. Increased cosmic rays produce increased ionization, which produces more cloud condensation nuclei, which produces more low-level cloud cover, which reflects more sunlight back to space, which cools the planet. The evidence for this cosmic ray climate connection remains mixed. Laboratory experiments at CERN, using particle accelerators to simulate cosmic ray ionization, have demonstrated that ionization can indeed enhance nucleation of sulfuric acid particles that could grow into cloud condensation nuclei. But the atmospheric conditions under which this effect actually influences cloud cover are constrained, and observational studies have found varying results when attempting to correlate cosmic ray flux with cloudiness. The 11-year solar cycle produces roughly 15% variation in cosmic ray flux at Earth, and some studies have found correlations between this variation and climate parameters, while others have not. What is less disputed is that a heliospheric compression producing tenfold or greater increases in cosmic ray flux would dwarf the variations produced by the solar cycle. Even if the cosmic ray cloud connection is weak under normal conditions, it could become significant under extreme compression scenarios. A sustained increase in global cloud cover would alter the planetary energy balance, potentially triggering or enhancing glaciation. The late Ordovician extinction mentioned earlier was associated with glaciation, and if cosmic ray-induced cloud changes contributed to that glaciation, the mechanism provides a plausible physical link between heliospheric compression and mass extinction. The chemical effects of enhanced cosmic ray flux extend into the troposphere as well. Nitrogen oxides produced by spallation reactions would not remain confined to the stratosphere. Atmospheric circulation would mix them downward, contributing to acid rain formation and affecting air quality globally. The quantities involved are smaller than industrial nitrogen oxide emissions in modern times, but they would be distributed globally rather than concentrated near industrial centres, and they would persist for as long as the compression continued. Ecosystems already stressed by increased radiation, UV exposure, and potential climate change would face additional chemical stress from the altered atmospheric composition. The interaction effects between these mechanisms create the potential for nonlinear responses. Ozone depletion allows more UV radiation to reach the troposphere, where it can drive photochemical reactions that affect air quality and vegetation. Climate cooling reduces atmospheric water vapor, which is itself a greenhouse gas, potentially amplifying the cooling. Reduced primary productivity decreases the biosphere's carbon uptake, affecting the long-term carbon cycle. Stress on ecosystems reduces their resilience, making them more vulnerable to other perturbations. A severe heliospheric compression would not produce a single discrete effect, but a cascade of interacting consequences that could push the Earth system into a different state. The paleontological record hints at such cascades. The mass extinctions of the past did not typically result from single, simple causes. The Permian extinction, 252 million years ago, the most severe in Earth's history, involved volcanism, global warming, ocean acidification, anoxia, and possibly other factors whose contributions remain debated. The Cretaceous-Paleogene extinction that killed the non-avian dinosaurs 66 million years ago began with an asteroid impact, but also involved massive volcanism in India, whose relationship to the impact and extinction remains unclear. Extinctions appear to occur when multiple stresses coincide or cascade, overwhelming the resilience that ecosystems normally demonstrate. A severe heliospheric compression, lasting thousands of years, could provide exactly such a cascade of stresses. Enhanced radiation damages DNA and increases mutation rates. Ozone depletion increases UV exposure and kills sensitive organisms. Climate cooling shifts habitats and stresses agricultural systems. Altered atmospheric chemistry affects plant growth and ocean productivity. Reduced primary productivity cascades through food webs. Species already pushed to the margins of their tolerances by any of these factors become vulnerable to extinction from any additional perturbation. The compression itself might not be sufficient to cause mass extinction, but it could weaken the biosphere to the point where other factors, a volcanic eruption, an asteroid impact, even the normal variability of climate, could trigger collapses that would not have occurred in a healthy system. This perspective reframes the heliosphere's role in Earth's history. The shield the Sun provides is not merely a barrier against immediate radiation hazards. It is a stabilizing influence that prevents the accumulation of stresses that could destabilize the biosphere over geological time. When that shield weakens, the Earth does not immediately die, but it becomes more vulnerable, less able to absorb perturbations, more likely to be pushed across thresholds into states hostile to the life that has evolved under protected conditions. The current state of the heliosphere provides a baseline against which to measure these vulnerabilities. The Voyager spacecraft, having crossed the heliopause and entered interstellar space, continue to return data on the conditions just outside the heliosphere. They report that the interstellar magnetic field is stronger than expected, and that the boundary between the heliosphere and the interstellar medium is more dynamic than models had predicted. The heliopause does not hold steady at a fixed distance, but fluctuates in response to variations in both the solar wind and the interstellar pressure. The Voyager data reveal a boundary that is constantly adjusting, negotiating, responding to the balance of forces that maintain it. The Interstellar Boundary Explorer, or IBEX, a spacecraft launched in 2008 that maps the heliospheric boundary by detecting energetic neutral atoms, has discovered structures in the heliosphere that were not anticipated. The IBEX ribbon, a narrow band of enhanced emissions that arcs across the sky, appears to be produced by the interaction between the heliospheric and interstellar magnetic fields in ways that are still being understood. The heliosphere's shape is not the simple comet-like form that early models predicted, but a more complex structure influenced by magnetic field draping, plasma instabilities, and the local inhomogeneities of the interstellar medium. This complexity means that predictions about how the heliosphere would respond to a dense interstellar cloud carry significant uncertainties. Models of heliospheric compression under various interstellar conditions have been developed, but they necessarily involve simplifications. The real interstellar medium is not uniform but clumpy, with density variations on scales from light years down to astronomical units. A molecular cloud is not a smooth density enhancement, but a turbulent, magnetized, structured medium with filaments, cores, and envelopes. The heliosphere entering such a cloud would not experience a simple, uniform pressure increase, but a chaotic, time-varying environment that could produce compression and relaxation cycles over timescales of years to decades. The average compression might be severe, but the fluctuations could produce spikes in cosmic ray flux, even beyond what the average would suggest. The Sun's passage through the galaxy is carrying the solar system toward an encounter with denser interstellar material. The local interstellar cloud is finite, and the Sun will exit it within the next few thousand years. Beyond it lies the G cloud, another warm, partially ionized cloud of similar properties, but beyond the local complex of clouds lies denser material. The Scorpius-Centaurus Association, a group of young stars roughly 400 light-years away, is surrounded by expanding shells of gas from supernova explosions. The local bubble itself was carved by these supernovae over the past 10 to 20 million years. The edges of the local bubble mark the transition to denser interstellar material that the Sun will eventually encounter. The timescales are long by human standards, hundreds of thousands to millions of years before the Sun reaches significantly denser regions, but they are short by geological standards. The solar system has passed through such regions many times in Earth's history, and it will do so again. The question is not whether heliospheric compression will recur, but when and how severe, and whether human civilization will still exist to face it. That last question introduces a dimension of vulnerability unique to the present era. For 4 billion years, life on Earth has experienced heliospheric compressions without technological civilization being at risk. Evolution does not preserve individuals. It preserves populations that can adapt and survive over generations. A compression lasting a few thousand years is brief by evolutionary standards, enough time for selection to favour radiation resistance, for populations to shift to less exposed habitats, for the biosphere to adjust through the mechanisms that have sustained it through previous events. Human civilization operates on different timescales. Our technologies, our infrastructure, our economic and political systems are calibrated to decades, not millennia. A sustained crisis lasting thousands of years would outlast nations, ideologies, and perhaps the continuity of technological knowledge itself. The radiation effects of a severe compression would be chronic rather than acute, raising cancer rates and developmental abnormalities across generations without the dramatic immediacy of a nuclear war or asteroid impact. The slow accumulation of damage could erode institutions gradually, making it difficult to sustain the coordinated response a multi-millennial crisis would require. And there are specific technological vulnerabilities that would not have existed in any previous compression. Modern civilization depends on satellites for communication, navigation, weather monitoring, and global coordination. Satellites in Earth orbit are partially shielded by the magnetosphere, but are far more exposed to cosmic radiation than the surface. Enhanced cosmic ray flux would increase the rate of single-event upsets, errors caused by energetic particles striking sensitive electronics, and accelerate the degradation of solar panels, sensors, and structural materials. The satellite infrastructure that coordinates global civilization could become unreliable or require much more frequent replacement, straining the resources of spacefaring nations during a period when other stresses would be competing for attention. The power grids that electrify civilization are vulnerable to geomagnetic disturbances caused by solar activity, as demonstrated by the 1989 Quebec blackout triggered by a solar storm. The enhanced cosmic ray flux during heliospheric compression would not directly cause geomagnetic storms, but the compression dynamics could alter the magnetosphere's response to solar wind variability, potentially creating new vulnerabilities. More directly, the electronics that control power generation, transmission, and distribution could experience increased failure rates from cosmic ray-induced damage, requiring redesign or hardening of critical systems. These technological vulnerabilities introduce feedback loops that could amplify the primary stresses. A society struggling with increased disease burden, reduced agricultural productivity, and climate disruption would be poorly positioned to maintain and adapt the complex technological systems that modern life depends on. The resilience that allowed previous biospheres to survive compressions might not extend to a technological civilization that has substituted engineered systems for natural redundancies. Yet awareness is itself a form of resilience. Unlike any previous species, humans can understand the threat, monitor its approach, and prepare responses. The same scientific enterprise that revealed the heliosphere's existence and vulnerability can track the Sun's motion through the interstellar medium, model compression scenarios, and develop mitigation strategies for the centuries before any dense cloud encounter. The mitigation strategies that human ingenuity might devise span a remarkable range, from the immediately practical to the speculatively transformative. Understanding these potential responses requires first appreciating what can and cannot be changed about the fundamental situation. The heliosphere's size is determined by the balance between solar wind pressure and interstellar medium pressure. Humans cannot meaningfully alter the density of an approaching interstellar cloud, nor can they redirect the solar system's trajectory through the galaxy. The Sun will encounter whatever material lies along its path, and the heliosphere will respond according to physics we can understand but not override. What remains within potential human influence falls into several categories: shielding and protection at the planetary and local level, adaptation of biological and technological systems to higher radiation environments, and the far more speculative possibility of artificially augmenting the heliosphere itself. The most immediate and practical category involves enhancing protection at Earth's surface and in near-Earth space. Earth's atmosphere already provides substantial shielding, equivalent to roughly 10 meters of water or nearly a meter of lead. This natural protection would continue during a compression event, though the secondary particle cascades from enhanced cosmic ray flux would increase radiation exposure at the surface. The magnitude of this increase depends on the severity of the compression and the energy spectrum of the galactic cosmic rays reaching the inner solar system. For moderate compressions, reducing the heliosphere to half its current size, surface radiation might increase by a factor of 2 to 3, a significant elevation but not immediately catastrophic for most organisms. Severe compressions bringing the heliopause inside Earth's orbit could increase surface radiation by an order of magnitude or more, fundamentally altering the radiation environment that surface life experiences. For such severe scenarios, shielding at the local level becomes essential. Underground construction provides excellent radiation protection, with each meter of rock or soil reducing cosmic ray flux substantially. Human civilization has extensive experience with underground construction, from mines and tunnels to subway systems and bunkers. Expanding this infrastructure to provide radiation-protected spaces for living, working, and food production would be technically straightforward, though enormously expensive and disruptive if implemented on the scale necessary to shelter significant populations. The ancient practice of cave dwelling, which humans abandoned as civilization developed, might find new relevance in a high-radiation future. Agricultural systems would require particular attention. Crops grown outdoors would be exposed to enhanced radiation, potentially suffering genetic damage, reduced yields, and increased mutation rates that could destabilize food production. Underground or heavily shielded agricultural facilities using artificial lighting could maintain food production regardless of surface radiation levels, but the energy requirements would be enormous. Current estimates suggest that fully indoor agriculture using artificial lighting requires roughly 10 times more energy per calorie produced than traditional outdoor farming. Scaling this to feed billions would demand energy production capacity far beyond current levels, likely requiring a massive expansion of nuclear power or fusion energy if that technology becomes practical. The transition to protected agriculture would need to begin long before a compression event reached its peak, as building the necessary infrastructure would require decades or centuries of sustained effort. Water supplies present different challenges. Surface water bodies would accumulate radioactive isotopes produced by cosmic ray interactions with the atmosphere, particularly carbon-14 and tritium. Groundwater, shielded by overlying rock and soil, would remain largely uncontaminated by new isotope production, though existing groundwater reserves are finite and often slow to recharge. Desalination of seawater combined with storage in shielded reservoirs could provide protected water supplies, but again at substantial energy cost. The interdependence of food, water and energy systems means that addressing any one vulnerability requires addressing all of them simultaneously. The satellite infrastructure that modern civilization depends on would face more immediate challenges than surface systems. Spacecraft operate outside Earth's atmospheric shielding and receive only partial protection from the magnetosphere, depending on their orbital altitude and inclination. Satellites in low Earth orbit benefit from some magnetic shielding, but still experience much higher radiation levels than the surface. Satellites in geostationary orbit, where most communication satellites operate, are largely outside the protective magnetic field and would experience radiation increases roughly proportional to the heliospheric compression. The enhanced particle flux would increase the rate of single event effects, upsets, latch-ups, and burnouts caused by energetic particles striking sensitive electronics. Current satellite designs incorporate radiation hardening and error correction to handle the existing space radiation environment. But these designs assume heliospheric modulation at roughly current levels. A significantly compressed heliosphere would require redesigned electronics with greater radiation tolerance, increased shielding mass that would raise launch costs, and more frequent replacement of spacecraft as accumulated radiation damage shortened operational lifetimes. The economic implications of maintaining satellite infrastructure through a compression event would be substantial. Current satellite manufacturing capacity produces hundreds of spacecraft annually, but maintaining current capabilities through tenfold higher radiation might require manufacturing thousands of replacements per year, with each spacecraft being more expensive due to radiation hardening requirements. The cost of maintaining global communications, navigation, and Earth observation capabilities could multiply dramatically, potentially forcing difficult choices about which capabilities to preserve and which to abandon. A society already stressed by the direct effects of enhanced cosmic radiation might struggle to allocate resources to maintaining its space infrastructure, potentially triggering a retreat from space-dependent technologies that would compound other difficulties. These terrestrial and near-space challenges, while formidable, fall within the realm of conventional engineering responses to environmental stresses. More speculative approaches contemplate intervening in the heliosphere itself, augmenting the Sun's natural shield or creating artificial barriers to cosmic radiation. Such approaches would require manipulating energies and scales far beyond current technological capabilities, but they are not obviously forbidden by physics, making them legitimate subjects for long-term consideration. The heliosphere's protective effect arises from the solar wind's magnetic field, which deflects and modulates incoming charged particles. Artificially enhancing this effect would require either increasing the solar wind output, strengthening its magnetic field, or creating an artificial magnetic structure that could substitute for or supplement the natural heliosphere. Direct manipulation of solar output is so far beyond current or foreseeable technology that it borders on the fantastical. The Sun releases roughly 4 million tons of matter per second as solar wind, carrying roughly 1 billion watts of kinetic energy. Meaningfully augmenting this output would require delivering comparable energy to the solar corona, an intervention that would demand harnessing a significant fraction of the Sun's total luminosity and somehow directing it to enhance wind production. The engineering challenges are so extreme that this approach seems relegated to the very long-term future, if it is possible at all. Creating artificial magnetic structures in interplanetary space presents somewhat more tractable, though still enormous challenges. A magnetic shield positioned at the heliopause would need to deflect charged particles across a surface area of billions of square kilometers. Even a very thin magnetic field requires substantial current-carrying infrastructure to generate. Superconducting coils in space could theoretically create strong magnetic fields with minimal power consumption once established. But the sheer scale of infrastructure required to shield even a fraction of the heliospheric boundary would dwarf any construction project in human history. A more modest approach might position magnetic shields at specific locations to protect high-value assets, such as a magnetic shield at the Sun-Earth Lagrange point that could deflect particles heading toward Earth. But the dynamics of charged particle motion in complex magnetic fields make it unclear whether such localized shields could provide meaningful protection against the diffuse cosmic ray flux that a compressed heliosphere would emit. Another speculative approach involves not blocking cosmic rays but detecting and warning about particularly intense bursts of radiation that might accompany compression events. The cosmic ray flux is not perfectly constant, but varies with solar activity and interstellar conditions. During heliospheric compression, there might be periods of particularly intense radiation associated with interactions between the compressed heliosphere and variable features of the interstellar medium. A network of particle detectors positioned throughout the inner solar system could provide advance warning of such intensity spikes, allowing populations to seek shelter and sensitive systems to be powered down or protected. This monitoring capability exists in rudimentary form today, with spacecraft throughout the solar system detecting particle environments, but expanding it to provide reliable forecasting would require understanding compression dynamics in far greater detail than current models provide. The timescales involved in potential future compressions provide humanity's greatest strategic advantage. The Sun's motion through the galaxy can be tracked with increasing precision as astronomical measurements improve. The location and density of interstellar clouds along the Sun's future trajectory can be mapped using observations of background starlight, interstellar absorption lines, and direct measurements by spacecraft venturing toward the heliosphere's edge. Current knowledge suggests the Sun will remain within the relatively clear local bubble for at least another 100,000 years, possibly several 100,000, before encountering significantly denser material. This timescale, while short by geological standards, is long by historical standards. 100,000 years ago, modern humans were just beginning to spread out of Africa. 100,000 years from now, if technological civilization persists and develops, its capabilities may be as far beyond current technology as current technology is beyond stone tools. The interstellar probes that humanity has already launched provide the foundation for more ambitious monitoring efforts. Voyager 1 and Voyager 2, launched in 1977, have crossed the heliopause and are now making direct measurements of the interstellar medium, though their instruments are failing after more than 4 decades of operation. The New Horizons spacecraft, which flew past Pluto in 2015, continues outward and may eventually provide additional data on the outer heliosphere and nearby interstellar space. Future dedicated missions to the heliospheric boundary could carry more advanced instruments designed specifically to characterize the interstellar environment and monitor the heliosphere's response to varying conditions. Proposals for interstellar precursor missions have been discussed since the 1970s. A spacecraft sent to a distance of several hundred astronomical units, far beyond the heliopause, could study the unmodified interstellar medium and observe the heliosphere from outside. Such a mission using current propulsion technology would require decades to reach its destination, but the scientific return would include direct measurements of the galactic cosmic ray environment that Earth would experience during severe heliospheric compression. More ambitiously, a network of monitoring stations distributed throughout the outer solar system and nearby interstellar space could provide continuous surveillance of approaching interstellar material, giving centuries or millennia of warning before any significant compression event. The detection of dense interstellar clouds that might cause severe compression is already possible using ground-based and space-based telescopes. The local interstellar cloud, which the Sun is currently traversing, was discovered through its effects on starlight passing through it. Similar techniques can identify denser clouds at greater distances, mapping the interstellar terrain the Sun will travel through over coming millions of years. The resolution and sensitivity of these maps will improve as astronomical instrumentation advances, eventually providing detailed forecasts of heliospheric conditions far into the future. This forecasting capability, combined with the long timescales before any severe compression is likely, means that humanity could potentially have tens of thousands of years to prepare for a major compression event if the civilization that develops the forecasts persists long enough to act on them. The question of civilizational persistence over such timescales is itself one of the most profound challenges any species can face. Human civilization in its current form is roughly 10,000 years old, dating from the agricultural revolution that enabled settled societies. Technological civilization capable of space exploration is barely a century old. No human institution has survived for 100,000 years. No organized human activity has maintained coherence across such timescales. The warning time that astronomy can provide is only valuable if the civilization receiving the warning can sustain a coordinated response across the entire interval. Historical examples of long-term human projects provide limited guidance. The Gothic cathedrals of medieval Europe took centuries to complete, with construction spanning multiple generations of builders who never saw the finished structures. The maintenance of irrigation systems in ancient Mesopotamia required coordination across centuries, as the gradual silting of canals demanded continuous dredging and occasional major reconstruction. But even these examples span at most a few centuries, not the tens of thousands of years that might separate warning from event in a heliospheric compression scenario. The challenge is not merely technological, but cultural and institutional, requiring mechanisms for transmitting knowledge, maintaining motivation, and coordinating action across timescales that dwarf all previous human experience. Various proposals have been advanced for transmitting important information across very long timescales. The nuclear semiotics program of the 1980s and 1990s attempted to design warning markers for nuclear waste repositories that would remain interpretable for 10,000 years, encountering the fundamental difficulty that languages, symbols, and cultural contexts change unpredictably over such intervals. The Long Now Foundation's initiatives including the 10,000-year clock under construction in Texas, aim to foster long-term thinking but have not yet demonstrated persistence across even a small fraction of their target timescale. The challenge of maintaining awareness of a heliospheric compression threat across 100,000 years would require institutions and practices that do not yet exist, and whose design is itself a research problem of considerable difficulty. Yet the very awareness of this challenge represents a form of progress. Previous generations could not have known about the heliosphere's vulnerability because they could not have known the heliosphere existed. The scientific understanding that reveals the threat also reveals the possibility of response. Each generation that advances astronomical knowledge, improves interstellar medium mapping, and develops the technologies for space-based radiation, protection contributes to a cumulative capability that might eventually prove adequate to the challenge. The question is whether this cumulative progress can continue long enough to matter. The biological resilience that carried life through previous compression events remains a foundation that technological civilization can build upon. Humans are not starting from zero in facing enhanced radiation environments. The DNA repair mechanisms that evolved over billions of years provide baseline protection that technological augmentation can enhance rather than replace. Medical interventions that reduce cancer risk, genetic modifications that improve radiation resistance, and pharmaceutical approaches that enhance DNA repair are all active areas of research, with applications to radiation protection. The next century will likely see substantial advances in human biological resilience to radiation, driven partly by the needs of space exploration and partly by the general advance of biomedical science. Agricultural systems can similarly be enhanced through biotechnology. Radiation-resistant crop varieties could maintain yields in environments that would devastate current cultivars. Plants with enhanced DNA repair mechanisms or with genetic redundancy that buffers against radiation-induced mutations could form the basis of food production systems robust to enhanced cosmic ray flux. The development of such varieties could begin long before any compression threat materializes, as the same traits that provide radiation resistance often confer resistance to other environmental stresses. A research program aimed at radiation-resistant agriculture would have immediate applications to climate adaptation and sustainable farming, making it valuable regardless of heliospheric conditions. The integration of biological and technological approaches offers perhaps the most robust path to long-term resilience. A civilization that has enhanced both its biological radiation resistance and its technological shielding capabilities would be far more resilient to heliospheric compression than one relying on either approach alone. The redundancy provided by multiple independent protective mechanisms reduces the risk that any single failure could prove catastrophic. This principle of defense in depth, well established in engineering safety practice, applies equally to existential risks from cosmic radiation. The psychological and social dimensions of preparing for a threat that may not materialize for tens of thousands of years present their own challenges. Human motivation is calibrated to timescales of years to decades, not millennia. The discounting of future benefits that drives much of economic decision-making means that investments with payoffs in the distant future appear nearly worthless from the perspective of current decision-makers. Overcoming this psychological barrier requires reframing the challenge, perhaps by emphasizing the immediate benefits of research that also serves long-term preparedness, or by cultivating values that extend concern to descendants many generations removed. Some philosophical and religious traditions provide frameworks for such extended concern. The concept of seven-generation stewardship, attributed to the Haudenosaunee Confederacy, asks decision-makers to consider the effects of their actions on descendants 7 generations in the future, roughly 150 to 200 years. Extending this principle further back in time, and much further forward, could provide an ethical foundation for very long-term planning. The philosophical tradition of long-termism explicitly argues for giving substantial moral weight to the welfare of future generations, potentially very many generations extending across cosmic timescales. Whether such philosophical positions can motivate sustained collective action remains an open question, but they at least provide a vocabulary for discussing why such action might matter. The scientific enterprise itself embodies a form of long-term thinking that transcends individual lifetimes. The observations of Tycho Brahe in the 16th century enabled Johannes Kepler's derivation of planetary motion laws in the 17th century. which in turn enabled Isaac Newton's gravitational theory that remained the foundation of celestial mechanics for over 2 centuries. Each generation of scientists builds on the work of predecessors and creates foundations for successors. Extending this cumulative enterprise to address heliospheric challenges would require maintaining scientific institutions and practices across timescales far longer than the few centuries of modern science, but the basic model of cumulative progress is already established. The exploration of the outer solar system and interstellar space will continue to refine understanding of the heliosphere and its interactions with the galactic environment. Each mission to the outer planets returns data on the solar wind's behaviour at different distances from the Sun. Each observation of interstellar absorption lines maps more of the material the Sun will eventually encounter. Each improvement in theoretical models of heliospheric dynamics sharpens predictions of how compressions would unfold and what their consequences would be. This gradual accumulation of knowledge, extending the work that Eugene Parker began in 1958, represents humanity's first steps toward understanding and eventually managing its relationship with the galactic environment. The transition from purely scientific understanding to practical preparedness would mark a new phase in human civilization's relationship with cosmic threats. For most of human history, the cosmos was either ignored as irrelevant to daily life or worshipped as the domain of gods beyond human influence. The scientific revolution revealed the cosmos as comprehensible, subject to natural laws that human inquiry could discover. The space age demonstrated that the cosmos was also accessible, a realm humans could enter and explore. The recognition of heliospheric vulnerability points toward a further transition in which the cosmos becomes not just comprehensible and accessible, but manageable, a domain where human action can shape outcomes that matter for human welfare. This transition, if it occurs, will require developments both technological and cultural. The technologies for space-based radiation monitoring, for terrestrial shielding and protected agriculture, for biological radiation resistance are all extensions of current capabilities that continued progress will likely provide. The cultural developments, the institutions for very long-term planning, the values that extend concern to distant descendants, the coordination mechanisms that can sustain effort across millennia are less certain. These capabilities must be invented, not merely extended from current practice. The challenge is not beyond human capability, it is merely beyond human experience. Nothing in the physics of heliospheric compression or cosmic radiation makes the challenge insuperable. The energies involved, while enormous by human standards, are not so overwhelming that technological intervention is impossible in principle. The timescales, while long by historical standards, are not so compressed that preparation is impossible if begun in time. What is required is sustained attention to a problem that is real but not yet urgent, important but not yet immediate. Whether human civilization can maintain such attention across the timescales required remains the central uncertainty. The evidence that such attention can be sustained exists, scattered through human history like seeds waiting for the right conditions to germinate. The cathedrals of medieval Europe took generations to complete, their architects knowing they would never see the finished spires. The great irrigation systems of ancient China required centuries of maintenance and expansion, each generation accepting responsibility for infrastructure they had inherited and would bequeath. The libraries of the ancient world, from Alexandria to the great repositories of Buddhist texts in cave temples, represented investments in preserving knowledge for readers not yet born. These precedents demonstrate that humans can organize collective efforts, extending beyond individual lifespans when the cultural conditions support such organization. The task now is to create such conditions for a challenge that operates on timescales longer than any previous human undertaking. The heliospheric shield has protected Earth for billions of years without any conscious effort on humanity's part. This protection has been a cosmic gift, as unearned as the warmth of sunlight or the stability of planetary orbits. The recognition that this gift may be periodically withdrawn, that the galactic environment imposes its own rhythms on solar system habitability, transforms the relationship between humanity and its cosmic context. We are not merely passive beneficiaries of favourable conditions, but potential agents in maintaining those conditions through periods when natural processes fail to provide adequate protection. This agency carries with it a new form of responsibility. If humanity possesses the capability to predict heliospheric compressions, and to take actions that would protect life through such compressions, then the failure to develop and exercise that capability becomes a moral failure, not merely a technical one. The ancestors who first controlled fire did not choose that responsibility. It emerged from capability. The generations who first split the atom did not choose the responsibility that came with nuclear weapons. It emerged from knowledge. Similarly, the understanding of heliospheric dynamics and their potential consequences creates a responsibility that did not exist before such understanding was possible. The precise nature of this responsibility remains to be defined. Does it extend only to human welfare, or to all terrestrial life that would be affected by heliospheric compression? Does it extend only to generations now living and their immediate descendants, or to all future generations who might exist if civilization successfully navigates such challenges? Does it prioritize maintaining current forms of life and civilization, or does it permit or even require transformation of those forms to better withstand cosmic threats? These questions have no easy answers, but they have the virtue of being the right questions, the ones that must be addressed if humanity is to develop a mature relationship with its galactic environment. The monitoring infrastructure that would enable prediction of heliospheric threats represents perhaps the most immediately actionable response to this new understanding. The two Voyager spacecraft, now beyond the heliopause, provide only 2 data points in an immense 3-dimensional volume of space. The heliosphere's nose and tail, its flanks and its complex interior structure all remain poorly characterized. A network of probes distributed throughout the outer solar system and into nearby interstellar space would provide the spatial coverage needed to detect approaching dense regions of the local interstellar medium years or decades before they reach the heliospheric boundary. Such a network would be expensive by current standards of space exploration, requiring dozens of spacecraft with decades-long mission lifetimes. But the cost would be modest compared to the potential consequences of encountering a dense cloud without warning. The data from such a network would need to flow into theoretical models capable of translating measurements of approaching interstellar material into predictions of heliospheric response. These models must capture the complex magneto-hydrodynamic interactions between the solar wind and inflowing galactic material, accounting for the solar cycle's variations, the heliosphere's asymmetric structure, and the turbulent processes that operate across a vast range of scales. Current computational capabilities are barely adequate for such modelling, but the exponential growth in computing power that has characterised the past several decades, if continued, would provide the capabilities needed. More challenging than raw computing power is the development of the physical understanding necessary to construct accurate models. This understanding will come only from observation, creating a feedback loop in which better data enables better models, which in turn guide the placement of sensors to gather still better data. The timeline for developing such monitoring capability extends across generations. The outer solar system is not easily accessible. Voyager 1 required 35 years to reach the heliopause, travelling at speeds that represent the upper limit of current chemical propulsion technology. A comprehensive monitoring network would require either many decades of patient deployment using conventional propulsion or the development of faster propulsion systems that could place sensors throughout the outer solar system within individual human lifetimes. Nuclear propulsion, solar sails, or more exotic technologies could reduce transit times from decades to years, but these technologies remain in early development stages. The decision to pursue such technologies, to fund the research and development that would bring them to operational status, must be made decades before the monitoring network they would enable could be deployed. This is the nature of very long-term planning. Decisions made now constrain options available to future generations, who must live with the consequences of our choices. Even with adequate monitoring, the question remains of what actions could be taken in response to an approaching heliospheric compression. The passive adaptations previously discussed, the underground refuges and radiation-hardened agricultural systems, represent one class of response. These are essentially acceptance strategies, acknowledging that the heliosphere will be compressed and preparing to endure the consequences. But the physics of the heliosphere also permits more active interventions, strategies that would seek to maintain the shield's protective capacity, even in the face of denser galactic material. The heliosphere is powered by the Sun, its size and strength determined by the balance between solar wind pressure and the pressure of the surrounding interstellar medium. Increasing solar wind pressure would push back against encroaching interstellar material, maintaining a larger heliospheric cavity even as external pressure increases. The Sun's output is not directly controllable by any technology foreseeable in the near term, but the effective pressure of the solar wind depends not only on its source strength, but on how that strength is distributed in space. Concentrating solar wind in particular directions could create localized regions of enhanced heliospheric protection, even if the overall heliosphere contracted. The concept of stellar engineering, of modifying the behavior of stars through technological intervention, has been discussed in the scientific and speculative literature for decades. Most such discussions focus on energy extraction, the harvesting of stellar output for civilizational use, but the same principles that would enable energy extraction could potentially enable output modification, including modification of the solar wind. Large structures positioned near the Sun could redirect or concentrate the solar wind, creating artificial enhancements in heliospheric pressure at locations deemed most important for protection. The scale of such structures would be immense by current standards, requiring materials and construction capabilities far beyond present technology. But nothing in physics forbids such structures. They are engineering challenges, not physical impossibilities. A less ambitious form of active intervention would focus not on modifying the heliosphere globally, but on creating localized protective regions within a compressed heliosphere. Artificial magnetic fields generated by orbital or deep space structures could deflect charged particles from specific volumes of space, providing protection for spacecraft or even for planetary regions. The energy requirements for such localized shielding would be far smaller than those for global heliospheric modification, though still substantial by current standards. Superconducting magnets of unprecedented size and field strength would be required. The cooling systems to maintain superconductivity in the thermal environment of space would add further complexity. Yet all these technologies are extensions of existing capabilities, not fundamental departures from known physics. The protection of Earth specifically might be achievable through intervention at the scale of planetary magnetospheres, rather than the heliosphere as a whole. Earth's magnetic field already provides substantial protection against charged particles, but this protection would be overwhelmed during severe heliospheric compressions when galactic cosmic ray intensities increase by an order of magnitude or more. Enhancing Earth's magnetic field artificially could compensate for this increased flux, maintaining surface radiation levels within the range that terrestrial life has evolved to tolerate. Proposals for artificial magnetospheric enhancement have been studied primarily in the context of protecting spacecraft and astronauts during transit to Mars, where the planet's weak magnetic field offers little natural protection. Scaling such concepts to protect an entire planet would require enormous increases in the magnetic field strengths and volumes involved. But again, no physical law prevents such scaling. The most speculative proposals for active heliospheric management involve direct interaction with the interstellar medium itself. If an approaching dense cloud could be detected at sufficient distance, could actions be taken to disperse it or deflect it before it reached the heliosphere? The masses involved are staggering, far exceeding anything humanity could hope to move with conventional propulsion. But the clouds are not solid objects. They are diffuse accumulations of gas and dust held together by their own weak gravity and by the general pressure of the surrounding galactic medium. Introducing additional energy into such a cloud, whether through directed radiation, through collision with high-velocity projectiles, or through other means, could potentially disrupt its structure, reducing its density before it encountered the heliosphere. The energy requirements for such intervention would be astronomical in the literal sense, comparable to the output of stars rather than the output of human technology. Yet civilizations with access to significant fractions of stellar energy, which some theoretical frameworks suggest is a natural evolutionary state for technological species, might find such interventions feasible. These speculative technologies serve not as practical proposals but as existence proofs, demonstrations that the physics of heliospheric protection does not impose absolute limits on what intervention could achieve. Between the passive acceptance of heliospheric compression and the active management of galactic clouds lies a spectrum of possible responses, each with its own requirements of technology, energy, and social organization. The appropriate response for any given compression event would depend on its predicted severity, the preparation time available, and the capabilities that human civilization had developed by that point. A mild compression might require only enhanced radiation monitoring and modest agricultural adjustments. A severe compression might demand the activation of underground refuges and a fundamental reorganization of surface activity. An existential level compression might call for the deployment of active shielding technologies developed across generations of preparatory effort. The development of these capabilities would not occur in isolation from other trends in human civilization. The same technologies that would enable heliospheric monitoring and protection would also enable expanded space exploration, asteroid mining, and perhaps the establishment of human presence throughout the solar system. A civilization that had colonized the outer planets, that had developed the propulsion technologies and life support systems necessary for sustained activity in deep space, would find heliospheric monitoring a natural extension of its existing capabilities, rather than a specialized effort requiring separate justification. Similarly, the biotechnologies that might enable radiation-resistant crops and enhanced human radiation tolerance would be developed primarily for other purposes, for medicine and agriculture, and the enhancement of human capabilities, with application to heliospheric threats as a secondary benefit. This convergence of capabilities suggests that the development of heliospheric protection might be less a matter of dedicated effort than of general technological and civilizational advancement. A mature technological civilization, one that had realized even a modest fraction of the theoretical potential for space activity and biological engineering, would possess almost as a side effect the capabilities needed to detect and respond to heliospheric threats. The challenge becomes not so much developing specific technologies for this specific purpose, but rather sustaining the general trajectory of civilizational development that would naturally produce such technologies along with many others. Yet this optimistic view must be tempered by recognition that civilizational trajectories are not guaranteed. History is littered with civilizations that rose to impressive heights and then collapsed, their achievements lost and their capabilities degraded for generations or centuries. The Bronze Age collapse that devastated the Eastern Mediterranean civilizations around 1200 BCE, the fall of Rome that fragmented Europe for half a millennium, the societal collapses that overtook complex civilizations in the Americas and elsewhere, all demonstrate that progress is not inevitable. A civilization that suffered such a collapse at a critical moment, when preparation for an approaching heliospheric compression required sustained effort, might lose the capability to complete that preparation, facing the compression in a state of disorganization and technological regression. The robustness of civilizational capability against collapse thus becomes a factor in long-term heliospheric preparedness. Institutions that preserve knowledge and transmit it across generations, even through periods of instability, contribute to this robustness. Technologies that can be maintained and reproduced without requiring the entire apparatus of modern civilization contribute as well. The more redundancy and resilience built into the systems of knowledge and capability, the more likely that necessary preparations could continue even through periods of reduced civilizational capacity. This argues for a strategy of embedding heliospheric awareness into the deepest levels of human culture, making it part of the fundamental worldview that would persist, even if specific institutions and technologies did not. The cultural transmission of such awareness faces its own challenges. Human beings are adapted to attend to immediate threats and nearby opportunities, not to dangers that lie millennia or millions of years in the future. The psychological phenomenon of temporal discounting, in which future events are valued less than present events, is deeply embedded in human cognition, likely because it reflected adaptive responses to the ancestral environment, where long-term planning beyond a few seasons provided diminishing returns. Overcoming this bias to maintain genuine concern for very distant threats requires cultural institutions specifically designed to counteract natural psychological tendencies. Religious and spiritual traditions have historically provided frameworks for extending concern beyond the immediate present, connecting individual lives to larger cosmic narratives that span vast periods of time. The Hindu concept of cosmic cycles, the Buddhist notion of karma extending across lifetimes, the Abrahamic traditions of salvation history, all provide psychological mechanisms for caring about events beyond personal experience. Whether secular equivalents of these frameworks can provide similar motivation remains uncertain. The scientific worldview offers cosmic narratives of considerable grandeur. The story of cosmic evolution from the Big Bang through the formation of galaxies and stars and planets to the emergence of life and mind, but it is not clear that this narrative engages the motivational systems that drive sustained human effort in the way that religious narratives have historically done. The communication of heliospheric awareness to future generations must somehow bridge the gap between scientific understanding and visceral concern. The dangers are real, and the timescales are immense, but reality and immensity alone do not motivate action. What motivates action is connection, the sense that what happens matters, that future people whose welfare would be affected are somehow related to people now living. This connection can be established through biological descent, through cultural continuity, through identification with the human species as a whole, or through still broader identification with the community of all sentient life. Different individuals and cultures will establish connection through different mechanisms, and any effective strategy for sustaining heliospheric awareness must work through multiple mechanisms rather than relying on any single one. The scientific community itself will be crucial in maintaining technical understanding across the generations, but scientists alone cannot sustain the broader societal commitment that heliospheric protection would require. Artists, writers, filmmakers, and other shapers of cultural imagination will be needed to make the reality of heliospheric vulnerability vivid and compelling to audiences who will never read the technical literature. Political leaders and institution builders will be needed to translate cultural concern into policies and programs with real-world impact. Educators at all levels will be needed to ensure that each generation understands both the nature of the threat and the responses available. Religious and spiritual leaders may be needed to provide the motivational frameworks that sustain concern across timescales longer than individual lives. The coordination of all these actors toward a common purpose represents a challenge without clear precedent. Human civilization has achieved remarkable coordination in response to specific, immediate threats, mobilizing massive resources and reorganizing societies in wartime, for instance. But sustained coordination toward a diffuse, distant threat without the galvanizing effect of immediate crisis is far more difficult. The closest analogies might be the gradual development of international institutions and norms over centuries, the long campaigns that eventually abolished practices like slavery, or the multi-generational efforts to preserve cultural heritage through libraries, museums, and universities. These achievements suggest that sustained coordination is possible, but they also reveal how fragile such coordination can be and how easily it can be disrupted by shorter-term pressures. The question that remains, then, is not whether humanity possesses the technical capacity to survive a heliospheric compression event. We have seen that the physics, while daunting, is not insuperable. Detection is possible, mitigation is conceivable, adaptation lies within the realm of engineering imagination. The question that remains is deeper, more unsettling, and ultimately more revealing of what kind of species we are and what kind of species we might become. The question is whether humanity will choose to look outward, to attend to the invisible boundary that separates us from the hostile void, to maintain vigilance across the centuries and millennia that separate us from potential catastrophe. The question is whether we will remember. Consider what remembering would require. Somewhere in the unimaginable future, perhaps 3,000 years from now, perhaps 30,000, instruments that do not yet exist will register a perturbation in data streams we have not yet imagined. Particle counts will shift, magnetic field readings will fluctuate, radio emissions from the heliopause will change their character in ways that only trained specialists will recognize, and in that moment everything will depend on whether those specialists exist, whether the instruments have been maintained, whether the institutions that fund and coordinate heliospheric monitoring have survived the countless upheavals that human civilization will have endured in the intervening millennia. Everything will depend on whether the warning, once issued, is believed, on whether societies distracted by whatever concerns dominate that distant era can redirect attention to an invisible boundary beginning to contract somewhere beyond the orbit of Pluto, on whether the knowledge of how to respond has been preserved in forms that remain accessible and actionable. The chain of transmission that would connect present awareness to future action is almost impossibly long. It must pass through the rise and fall of nations, through technological revolutions that will make our current capabilities seem as primitive as stone tools, through cultural transformations that may render our languages dead and our concepts obsolete. It must survive dark ages if they come, maintain coherence through periods of abundance that might make vigilance seem unnecessary, persist through catastrophes that might absorb all available attention. And at every link in this chain, individual human beings must choose to learn what their predecessors knew, must choose to value what their predecessors valued, must choose to pass forward what they have received rather than allowing it to fade into obscurity. This is the deepest challenge posed by heliospheric vulnerability. Not the physics of interstellar particle radiation, not the engineering of planetary-scale magnetic shields, not even the detection of approaching density waves in the interstellar medium. The deepest challenge is the maintenance of knowledge, concern, and capability across timescales that dwarf the duration of any human institution that has ever existed. And yet, the very fact that we can pose this challenge, that we can recognize its dimensions and contemplate its requirements, represents something remarkable about the human species. For most of the history of life on Earth, organisms have responded to environmental pressures through the glacially slow process of genetic adaptation. A species either possessed the traits necessary to survive a changing environment or it did not. Those that did passed their genes forward. Those that did not went extinct. The process was blind, automatic, and utterly indifferent to the suffering it caused. No dinosaur contemplated the asteroid. No trilobite considered the coming anoxia. They simply lived, and then they died, and the universe proceeded without them. Humanity occupies a different position. Through the accident of evolution that gave us large brains and symbolic language, we have become a species capable of modelling our own future, of detecting threats before they arrive, of preparing responses to dangers that have not yet manifested. We have become, in a meaningful sense, the first species on Earth capable of choosing its own fate. This capacity is recent. It is fragile. It is far from guaranteed to persist, but while it exists, it opens possibilities that no previous form of terrestrial life has ever possessed. We can see the approaching cloud. We can understand what it means. We can decide what to do about it. This is not a small thing. In a universe that is, as far as we can determine, overwhelmingly dead and empty, the existence of a species capable of perceiving its own cosmic context and taking action to preserve itself represents something approaching a miracle. Not a supernatural miracle, not a violation of physical law, but a natural miracle, an emergence so improbable and so precious that its significance is difficult to overstate. The heliosphere that protects us from galactic radiation is not unique. Every star generates some form of stellar wind, and many stars likely produce magnetized bubbles around their planetary systems. But a heliosphere containing a species that knows it is being protected, that understands the mechanism of protection, that can detect when that protection is threatened, this may be vanishingly rare in the cosmos. Perhaps unique, we do not know. The local interstellar cloud through which we are currently passing will eventually give way to other regions of space. The solar system's velocity of approximately 26 kilometers per second never ceases. We are always moving, always encountering new conditions, always passing from one environment to another on timescales that make human history seem like the flicker of a firefly on a summer night. The cloud we will enter in perhaps 50,000 years may be denser than anything we have encountered in millions of years, or it may be no denser than what we experience now. The universe has not revealed its plans to us. It has only revealed that plans exist, that patterns govern the distribution of matter through the galaxy, and that our solar system must navigate those patterns whether we attend to them or not. What we do with this knowledge defines us. We could ignore it. The threat is distant enough that ignoring it would have no consequences for anyone now living, nor for their children, nor for many generations beyond. The psychological mechanisms that evolution installed in us actively encourage such ignoring, whispering that only the immediate matters, that the future can take care of itself, that worrying about events millennia hence is a waste of cognitive resources better devoted to present concerns. These whispers are not irrational. They served our ancestors well in the ancestral environment where they evolved. But they are not adapted to the environment we now inhabit, an environment in which our actions can affect the welfare of people separated from us by chasms of time that would have been inconceivable to any previous human generation. The choice to attend to heliospheric vulnerability, to build the institutions and develop the technologies and sustain the cultural practices that long-term protection requires, is a choice to become something new. Not post-human in the sense of technological transcendence, but more fully human in the sense of actualizing capacities that have lain dormant within our species since the first human beings looked up at the stars and wondered what they were. We have always been capable of long-term thinking. We have always been capable of caring about descendants we will never meet. We have always been capable of coordinating across generations to achieve goals no single lifetime could accomplish. But these capacities have been exercised only sporadically, only partially, only in the service of goals that now seem parochial compared to the challenges we face. The heliosphere invites us to something larger. It invites us to think of ourselves not as citizens of nations or members of ethnic groups or adherents of particular ideologies, but as inhabitants of a planetary system moving through a galaxy, protected by a magnetic bubble that neither knows nor cares about the distinctions that divide us. The cosmic radiation that would flood our world if the heliosphere were overwhelmed would not distinguish between rich and poor, between powerful and marginalized, between those whose ancestors have lived on this planet for millennia and those who arrived yesterday. It would simply irradiate, blindly, universally, with no respect for the categories by which we organize our social existence. There is something clarifying in this impartiality. It reminds us that the deepest challenges facing humanity transcend the boundaries we have constructed, that the ultimate threats to our existence come from sources that are genuinely indifferent to our self-imposed divisions. This does not mean that heliospheric awareness will automatically unify humanity. Nothing automatically unifies humanity. We are a quarrelsome tribal species, prone to seeing threats in each other more readily than in the cosmos. The history of human response to shared challenges is not particularly encouraging. Climate change, which poses threats on timescales of decades rather than millennia, has struggled to generate sustained global coordination, despite overwhelming scientific consensus. The prospect of threats on civilizational timescales is not more likely to galvanize action, simply because the stakes are higher. Indeed, the very remoteness of the threat may make it easier to ignore, easier to dismiss as someone else's problem, easier to sacrifice on the altar of more immediate concerns. And yet there are reasons for measured hope. The very fact that you are attending to these words, that you have followed this exploration from its beginning, through the physics of stellar winds and interstellar clouds, to this moment of reflection on what it all means, suggests that human beings are capable of caring about things that matter, even when they do not immediately affect us. The institutions of science, for all their flaws and limitations, have demonstrated a remarkable capacity to accumulate knowledge across generations, to correct errors, to gradually extend human understanding into domains that would have been unimaginable to earlier generations. The libraries and archives and museums that preserve human cultural heritage have survived wars and revolutions and the collapse of empires, maintaining continuity of knowledge across disruptions that seemed at the time to end everything that mattered. These achievements do not guarantee that heliospheric awareness will be sustained across the timescales required, but they demonstrate that such sustenance is not impossible, that human beings have sometimes managed to value and preserve things that transcend their immediate interests. What is needed now is the decision to begin, not the completion of heliospheric defense, which lies far beyond current capabilities, not even a comprehensive plan for such defense, which would be premature given our limited understanding. What is needed is the decision to take the first steps, to treat the heliosphere as something worthy of attention and study, and eventual protection, rather than as an invisible abstraction of interest only to specialists. This decision can be made by individuals who choose to learn about their cosmic environment and to share what they learn with others. It can be made by educational institutions that include heliospheric science in their curricula. It can be made by funding agencies that allocate resources to the detection and monitoring of the interstellar medium. It can be made by space agencies that include heliospheric missions in their long-term plans. It can be made by artists and writers who make the reality of our cosmic situation vivid to audiences who might otherwise never encounter it. Each of these decisions is small in itself. None will directly prevent a heliospheric compression event or mitigate its effects, but together they constitute the beginning of something that could, across enough time and with enough persistence, grow into a genuine capacity for species-level self-protection. The longest journeys begin with single steps. The pyramids were built one stone at a time. The libraries that preserved classical learning through the medieval period were assembled one manuscript at a time. The scientific understanding that now allows us to comprehend our cosmic situation was developed one discovery at a time by individual human beings who chose to wonder about things that had no immediate practical relevance. the future that might contain a humanity capable of defending itself against heliospheric threats will be built the same way, through countless individual decisions that accumulate into collective capability. The Sun continues its orbit around the galactic centre, as it has for 4.5 billion years and will for billions of years more. The solar wind continues to flow outward, as it has since the Sun first ignited, creating the bubble that shields everything we know and love from the hostile radiation of the galaxy. The interstellar medium continues its complex dance of clouds and voids and density variations, shaped by supernova explosions and stellar winds and gravitational interactions too numerous to catalogue. And somewhere ahead, in a future we cannot precisely date but cannot reasonably doubt, lies a cloud denser than any our species has experienced, waiting with infinite patience for our arrival. We cannot know whether the civilization that exists when that encounter occurs will be recognisably related to our own. Perhaps it will be something we would barely recognise, transformed by technologies and experiences we cannot imagine. Perhaps it will have spread beyond the solar system entirely, rendering the heliosphere one habitat among many rather than the sole container of human existence. Perhaps it will have long since solved the engineering challenges of heliospheric protection, treating the approaching cloud as a minor inconvenience rather than an existential threat. Or perhaps it will be caught unprepared, its civilization having forgotten the warnings accumulated by earlier generations, its attention absorbed by concerns that seem more pressing, until suddenly they are not. The choice between these futures is not made in some distant era. It is being made now in every decision about what to value, what to study, what to preserve, what to transmit. The heliosphere asks nothing of us. It is not a conscious entity. It has no preferences, no hopes, no fears. It simply exists, a consequence of physical processes that would occur whether or not anything alive existed to benefit from them. But we can choose to recognize what it provides. We can choose to understand how it works. We can choose to monitor its condition and prepare for its possible compromise. We can choose to become, not passive beneficiaries of cosmic fortune, but active participants in our own survival. This choice is what distinguishes beings capable of self-determination from beings merely subject to the forces that act upon them. This choice is, in some sense, what it means to be fully human. The stars above us tonight appear fixed and eternal. The same stars that shone on the first human beings who looked up and wondered. But we know now what they did not, that we are moving through a universe of constant change, that the apparent stability of the heavens conceals a dynamism that operates on timescales beyond ordinary perception. We know that our sun is one traveller among hundreds of billions in a galaxy itself in motion, that every point in space has a history and a future different from its present, that the environment through which we pass is not a static backdrop, but an active participant in the story of life on Earth. This knowledge is burden and gift alike. Burden because it reveals vulnerabilities we might have preferred not to contemplate. Gift because it opens possibilities for action that ignorance would have foreclosed. The shield is invisible, but the comfort it gives this planet is very real. Every breath we draw, every sunrise we witness, every moment of ordinary existence we take for granted, occurs within the protection of a boundary most people will never think about. The heliosphere asks for no gratitude and would not receive it if offered. But gratitude is appropriate nonetheless, not to the heliosphere itself, but to the cosmos that permits such structures to exist, and to the cascade of circumstances that placed our planet within one. We are the beneficiaries of protection we did not earn and could not have created. The question is what we will do with this gift. Across the vast reaches of galactic time, countless worlds must have faced similar moments, must have moved through regions of space that tested whatever protections their stars provided. We do not know how many of those worlds harboured life. We do not know how many saw that life extinguished by the failure of cosmic shields they never understood. We know only that we are here, that we understand, and that understanding creates responsibility. The universe has placed in our hands, for the first time in the history of Earth, the knowledge necessary to participate consciously in our own cosmic fate. What we build with that knowledge will determine whether the human story continues through the ages ahead, or ends as so many stories must have ended, in silence and forgetting. The interstellar winds are patient. They have blown for billions of years and will blow for billions more. They do not hurry, They do not threaten, they simply exist, as the cosmic environment has always existed, indifferent to the hopes and fears of any being small enough to inhabit planets circling ordinary stars. But we are not required to be indifferent in return. We can look outward. We can remember what we have learned. We can build what must be built and pass forward what must be preserved. We can become, across the long ages, a species worthy of the cosmos that created us. The heliosphere will not protect us forever. Nothing will protect us forever. But for as long as protection remains possible, for as long as knowledge and will and capability can be sustained, we have the choice to try. That choice is what we leave to the future, not certainty, not guarantees. Just the choice, and the knowledge that makes choice meaningful, and the hope that those who come after will value what we valued and remember what we understood. The winds between the stars have blown since the first galaxies formed, carrying with them the debris of creation, the remnants of exploded stars, the raw material from which new worlds are born. Our solar system moves through these winds as it always has, shielded by the magnetic breath of our star, surrounded by a bubble that we now know exists and now understand and might, if we are wise and fortunate and persistent, learn to preserve. The universe makes no promises, but it offers possibilities. One of those possibilities is a humanity that survives, that grows, that eventually takes its place among the stars from which it came. This possibility depends on choices made not only by distant descendants, but by people living now, reading now, deciding now what to value and what to ignore. The heliosphere does not care whether we make the right choices. The cosmos does not care, but we can care, and in that caring lies everything.